The biggest airport megaprojects in history reshaped the skies and the cities beneath them. Spanning massive terminals, high-speed transport links, and multi-billion-dollar hubs, these engineering feats transformed how the world connects. In this documentary, we explore the scale and ambition behind aviation's most legendary builds and the global forces that made them possible. In the heart of the Arabian Desert, where sand stretches endlessly toward the horizon, there lies an airport so vast it could swallow entire cities. King Fahd International Airport, just outside Dammam, Saudi Arabia, isn't merely a transportation hub. It's a monument to scale, ambition, and the futuristic vision of a kingdom that dared to build big. At over 780 square kilometers, the airport's property makes it the largest in the world by land area. That's not a typo. It's larger than the entire country of Bahrain. But what makes King Fahd International truly extraordinary isn't just its size. It's the statement it makes, that Saudi Arabia isn't content to follow the pace of global infrastructure. It intends to set it. Opened to commercial traffic in the late 1990s, this megastructure was designed not only to serve the growing eastern province, but also to position the kingdom as a logistical and geopolitical crossroads. Dammam, with its proximity to the Persian Gulf and to vital oil installations, was the perfect place for such a venture. And this airport, carved out of the desert like a futuristic fortress, was built to handle millions of passengers a year, with room to grow even further. But numbers only tell part of the story. The architecture speaks volumes too. From its mosque, one of the most serene and striking features of the complex, to its sweeping terminal design, every part of the airport reflects a blend of modern engineering and cultural reverence. The main terminal, with its clean lines and monumental scale, is a physical metaphor for Saudi Arabia's pivot to the future while staying rooted in heritage. The sheer logistics of managing an airport spread across hundreds of square kilometers is a feat of engineering unto itself. Road networks, utility corridors, and support facilities stretch like a web over the arid landscape. Even with only a portion of the total land developed, the airport manages to operate efficiently, thanks to meticulous planning and cutting-edge control systems. Beyond the infrastructure lies the human element, the workers, planners, and engineers who've kept this mammoth operation running for decades in one of the most challenging climates on Earth. Heat, sand, and isolation have tested every part of this project, yet it remains a key artery for both domestic and international travel. As Saudi Arabia charts a new course under its Vision 2030 plan, aiming to diversify its economy and become a global hub for business and tourism, King Fahd International is poised to play an even larger role. With capacity upgrades, potential expansions, and its proximity to future smart cities, this desert giant is far from finished. There are airports that simply connect cities, and then there's Denver International, an airport that feels more like a myth, wrapped in fog, conspiracy, and raw, undeniable scale. Set against the jagged silhouette of the Colorado Rockies, Dian isn't just an air hub, it's a riddle in concrete, steel, and prairie wind. From the moment you approach, you realize this place is different. The terminal roof rises like a row of white peaks, a canvas of fabric stretched into spires that mimic the mountains beyond. It's both architectural poetry and functional design, a nod to the natural world in the middle of a high-tech frontier. But behind the beauty lies a beast of logistics and ambition. Denver International is the second largest airport in the world by land area. Spanning over 50 square miles, it's larger than Manhattan. That space isn't just empty fields, it's a calculated investment in the future. room to grow, room to reimagine what an airport can be. When Den opened in 1995, it did so after delays, budget overruns, and more than a little controversy. It replaced the old Stapleton Airport, not because Denver needed a slightly better facility, but because it needed to think bigger, radically bigger. At the time, few could have predicted how essential that gamble would become. Today, with air traffic climbing and cities swelling, that oversized footprint now looks like foresight. Operationally, it's a marvel. The runways, 6 in total, are set wide apart, allowing simultaneous takeoffs and landings in nearly any weather. This efficiency is crucial in Denver's unpredictable climate, where snowstorms can whip in with little warning. Beneath the surface, a vast tunnel system once built for an ambitious, but famously flawed, automated baggage system still snakes its way below ground. A reminder of how pushing boundaries doesn't always go smoothly. Yet what truly sets Denver apart isn't just the infrastructure, it's the atmosphere. This airport breathes mystery. From strange murals to the giant blue horse sculpture at the entrance, complete with glowing red eyes, Den has become a magnet for conspiracy theories and urban legends. Secret bunkers, underground facilities, coded art. It's all part of the lore. Whether you believe any of it or not, there's no denying the airport has a presence. But look past the shadows, and you'll see something else. A living symbol of Denver's evolution. The airport isn't just a pit stop between coasts. It's a launchpad into the American West. It connects the Rockies to the world, fuels the city's economic engine, and anchors Colorado's global reach. And it does all of that with an eye on what comes next. Den is currently in the midst of multi-billion-dollar expansions, new gates, modernized terminals, and advanced security systems. It's shedding some of its 90s skin and stepping boldly into the 21st century. But even as it transforms, that original ambition, that sense of scale and audacity, still lingers in the wide-open airfields and endless walkways. Some megastructures announce themselves with flair and drama. Others assert their dominance with pure functionality, and Dallas-Fort Worth International Airport is firmly in that second category. No gimmicks, no illusions. Just raw, calculated efficiency stretched across more than 17,000 acres of Texas soil. DFW isn't just an airport, it's a city in its own right. One of the busiest and largest in the world, this colossus was born out of necessity in the 1970s, when the explosive growth of the Dallas and Fort Worth Metroplex demanded a central hub that could handle not just regional travel, but global ambition. And what they built was far more than a regional stopover. It became a cornerstone of international aviation. From above, DFW resembles a sprawling grid of movement and metal. 5 terminals arranged like a set of looping limbs, each connected by an automated people mover that shuttles millions of passengers through a labyrinth of gates, shops, and jetways. But despite the scale, the airport's design is surgical. Flights arrive and depart with near-military precision. Runways stretch in parallel rows, 7 of them in total, optimized for simultaneous takeoffs and landings without delay, even in heavy traffic. There's a certain elegance to how DFW operates, even in its sheer enormity. It's not here to dazzle, it's here to move. Freight, people, ideas. This airport is a logistics engine as much as a transportation hub. American Airlines, headquartered right next door, turned it into a fortress hub, funneling connections across North America and deep into international airspace. DFW doesn't just serve Texas, it serves the world. But beneath the concrete and control towers, there's a deeper story. This is an airport born from rivalry and resolution. In the early days, Dallas and Fort Worth were locked in a competitive tug-of-war over air service, each city desperate to assert its own identity. DFW was the peace treaty, a bold compromise that said, instead of fighting, let's build something neither of us could do alone. And they did, on a scale that stunned the world. Even now, the airport continues to evolve. Terminal renovations, futuristic upgrades, sustainable energy projects, DFW is constantly expanding not just in size, but in ambition. It was one of the first airports in the world to achieve carbon-neutral status, and its strategic position has made it a vital node in the global supply chain, particularly as e-commerce and cargo operations explode. Yet despite its industrial heart, DFW isn't cold. Step into the terminals and you'll find live music, local cuisine, art installations, threads of Texas culture woven into the infrastructure. It's subtle, but it's there. The sense that this massive machine still remembers the people it was built to serve. They didn't just build an airport on the shores of the Black Sea. They carved a new future for a nation out of rock, sea, and ambition. The construction of Istanbul Airport, one of the most audacious infrastructure projects of the 21st century, was not just a matter of civil engineering. It was a national statement, a vision chiseled into existence with relentless speed and almost cinematic scale. From the very first shovel of earth, this project wasn't designed to follow global aviation standards. It was meant to redefine them. The site itself was a challenge from the start. A mix of former open-pit coal mines, wetlands, and unstable terrain that required millions of cubic meters of earth to be moved, compacted, and stabilized. This wasn't just land reclamation. It was land transformation on a continental scale. Thousands of workers labored around the clock, building not only runways and terminals, but the very ground those structures would stand on. The scale of the terminal alone is staggering. Designed to be the largest under a single roof anywhere on Earth, the main passenger terminal covers over 1 million square meters. Its skeleton is steel, its skin glass and aluminum, but its foundation is poured from unflinching confidence. Every beam, every column was part of a choreography measured in millimeters, but executed at megastructure scale. Construction teams sourced materials from all over Turkey and beyond, fueling a logistical operation that mirrored military precision. Concrete was poured by the ton, and cranes moved like clock hands over the site, some of them among the tallest and most powerful in the world. And at the heart of it all, the project had to maintain momentum in a political and economic climate that was, at times, deeply volatile. Timing was everything. The goal was clear from the start. Open fast, open big. Unlike projects that slowly build up capacity, Istanbul Airport was envisioned to make a splash from day one. That meant building not one, but multiple parallel runways right from the outset, designed to handle hundreds of flights a day with minimal delay. The air traffic control tower, with its sleek tulip-inspired silhouette, was one of the first structures to rise, signaling the pace and design sophistication the rest of the site would follow. Around it, a spiderweb of service roads, utility tunnels, fuel lines, and drainage systems had to be laid out with unerring accuracy. Every inch of the infrastructure was future-proofed to accommodate the long-term goal. Over 200 million passengers annually once all phases are complete. No corner of this site was spared from overachievement. The cargo facilities were built to rival dedicated freight airports, with massive warehouses and high-speed loading systems constructed at breakneck pace. The runway system, built across 4 phases, was designed not only for volume but for wind, direction optimization, weather resilience, and operational efficiency that could outpace even the world's most established airports. Drainage was a particular challenge, given the area's geography. Massive culverts and underground reservoirs were constructed to manage rainwater and prevent flooding, a vital concern in a place where the sea is never far and the weather can turn swiftly. Even power and data lines were installed with redundancy and scalability in mind, buried deep and routed through protected channels to safeguard against both overload and sabotage. When construction crews finally handed over the keys, what they left behind wasn't just an airport. It was a piece of infrastructure that looked less like a public utility and more like a declaration carved into the earth. The sheer act of building it, under such tight deadlines, across such difficult terrain, and on such a colossal scale, stands as one of the great modern feats of engineering. It's not just what was built, it's how it was done. Quickly, relentlessly, and without blinking in the face of impossible complexity. Few structures have ever emerged from the ground with such poetic symmetry and brutal precision as Beijing Daxing International Airport. Born from an urgent need to relieve pressure from the overcrowded Beijing Capital Airport, Daxing was never going to be just a supplement. It was designed from the start as a symbol of China's ascendancy in aviation, infrastructure, and high-speed construction. The plan was staggering. A brand new airport built from scratch in less than 5 years, capable of handling tens of millions of passengers annually, and anchored by one of the most architecturally complex terminal structures ever attempted. The site chosen was flat and unremarkable farmland in the Daxing district, but it was about to become the nucleus of a new economic corridor. Before a single column could rise, thousands of workers, engineers, and machines had to transform an empty stretch of land into one of the most interconnected transportation hubs on Earth. At the heart of the project was the terminal itself, a sweeping, starfish-like structure that pushed the boundaries of spatial design. The challenge wasn't just to make it beautiful, but to make it brutally efficient. A central node with 6 extending arms meant that all gates could be reached with a maximum walking distance of just a few hundred meters, radically improving passenger flow. But constructing such a layout meant tackling extreme technical complexity. The roof alone is an engineering spectacle, a vast, undulating canopy of steel and glass that required precision assembly down to the millimeter. Dozens of custom-fabricated joints, expansion mechanisms, and modular support systems had to be installed in perfect harmony to accommodate both structural loads and seasonal temperature swings. Massive steel trusses, each weighing dozens of tons, were hoisted into place in synchronized operations that resembled the choreography of a space mission more than a traditional building site. Underground, an entirely separate world was being constructed. Beneath the terminal, construction crews carved out a multi-level labyrinth of tunnels, utility corridors, and high-speed rail links, some of which were laid concurrently with the rising terminal structure above. Timing and sequencing were everything. Sections of the underground rail platforms had to be sealed and reinforced, even as excavations were still ongoing elsewhere. The integration of subway lines, intercity trains, and future maglev systems meant that crews were building not just for today's capacity, but for a future where the airport would sit at the heart of a mega-regional transport network. Every slab of concrete, every steel beam underground, had to be laid with total synchronization with the structural demands above ground. And all of it had to happen without pause. Construction logistics on this scale verge on the surreal. Materials were delivered with military precision, steel from multiple provinces, glass from high-performance manufacturers, and prefabricated components trucked in across thousands of kilometers. On-site coordination was controlled through centralized digital platforms, utilizing BIM, building information modeling, to track every component, system, and timeline in real time. Massive cranes, custom-built for the height and reach required, moved like slow, mechanical dancers across the worksite, while armies of workers labored beneath them in shifts that rarely stopped. The workforce was huge, tens of thousands at the peak of construction, yet safety records remained among the best in the region due to a combination of strict protocols and smart monitoring systems. Environmental considerations, too, were built directly into the construction process. Entire stormwater retention systems, solar panel arrays, and thermal insulation technologies were integrated from the beginning, not tacked on as afterthoughts. The runways, of which multiple were built in parallel, were laid with advanced materials designed to withstand decades of use and extreme weather conditions. Drainage systems were buried deep and wide, designed to handle Beijing's summer rains without compromising operations. Fuel systems, baggage conveyors, HVAC installations, all were constructed with a mind toward redundancy, modularity, and long-term resilience. Sometimes, the ground beneath a project tells its own story. For Suvarnabhumi Airport, that story began in the wetlands east of Bangkok, a flood-prone expanse known as Nong Neu Hau, or Cobra Swamp. Turning that swamp into the busiest aviation gateway in Thailand required not just engineering, but imagination on an almost mythic scale. Before the first beam could be raised, the land had to be tamed. Crews moved in with heavy machinery to carry out one of the most extensive ground stabilization efforts ever undertaken in Southeast Asia. The saturated, unstable soil demanded deep foundations, and tens of thousands of concrete piles were driven deep into the ground to support the immense weight of the terminal and its associated infrastructure. This foundational work took years, but it was critical. It was the invisible backbone that would allow the entire project to stand. As soon as the earth was secured, the race to construct the terminal complex began. At the center of the airport's design was the main passenger terminal, a behemoth of steel and glass that, when completed, ranked among the largest in the world under a single continuous roof. The architecture, sleek, curving, and inspired by Thai aesthetics, was as much an engineering feat as it was a visual statement. Erecting its monumental roof structure required custom fabricated trusses and steel arches, assembled on site with millimeter-level precision. These components weren't just massive, they were complex, with each one shaped to accommodate the terminal's signature wave-like profile. Teams worked in coordinated shifts around the clock, craning sections into place, welding, securing, and enclosing vast sections of the structure in a construction ballet that had to hit precise deadlines despite Bangkok's oppressive heat and monsoon rains. Logistically, the site was a challenge. Located more than 25 kilometers from the city center, every piece of equipment, every shipment of materials, had to be routed through carefully orchestrated supply chains. Specialized components, including miles of glass paneling and advanced HVAC systems, were brought in from around the world and integrated into a site that was changing daily. The baggage handling system alone required its own sub-project, spanning multiple levels and kilometers of track, sensors, and software. Even beneath the polished floors and soaring ceilings, the airport's skeleton was a dense network of mechanical systems, each one installed during a phase of construction that had to proceed without disrupting others. While much of the international spotlight shone on the passenger terminal, the runways were no less impressive. Constructed with precision, The dual runways were laid with reinforced concrete to handle heavy aircraft movements, and their drainage systems were meticulously engineered to mitigate the flood risks of the region. Massive underground water management channels and pumping systems were embedded throughout the airport's footprint, ensuring operational continuity even during Thailand's intense rainy season. Control towers, fire stations, maintenance hangars, all of it had to rise in synchronization, each piece playing a critical role in the final orchestration. In the final stretch of construction, coordination became paramount. Hundreds of contractors, thousands of workers, and dozens of subcontracted firms had to bring their work together into a seamless whole. Testing and commissioning were conducted on an enormous scale. Fire suppression systems, electrical grids, telecommunications, lighting, signage, all had to function flawlessly before a single flight could depart. And despite political upheavals and public scrutiny, the airport opened to commercial service with a sense of scale and ambition that left little doubt. This wasn't just a new airport. It was a milestone in Thailand's infrastructure history. Not every airport begins with a blank slate. Some rise out of the chaos of overburdened infrastructure, and others, like Shanghai Pudong International, are built with foresight, planned from the ground up to handle a future that had not yet arrived. In the 1990s, Shanghai's existing airport, Hongqiao, was bursting at the seams, hemmed in by the city's explosive growth. The answer wasn't to expand within, it was to build outward, toward the coast. What followed was a high-speed campaign to reclaim land from the East China Sea and erect one of the most strategically engineered air hubs in Asia. Construction began not on solid land, but on soft, low-lying tidal flats. These coastal mudlands presented a serious engineering challenge. To establish a stable foundation, workers undertook an enormous land reclamation effort. Millions of cubic meters of sand and earth were dredged, compacted, and layered to form a platform strong enough to carry the weight of runways, terminals, and supporting structures. To prevent long-term subsidence, a real threat in such terrain, engineers employed deep piling techniques and advanced geotextile stabilization systems. It wasn't just about laying the groundwork. It was about making sure that groundwork could last for decades under the pressure of non-stop air traffic. Once the land was stabilized, Pudong's first phase was fast-tracked into reality. The master plan was modular and scalable, with future expansion built into the DNA of the project. Terminal 1, with its long, linear design, was constructed to handle the rising wave of international traffic, linking China's financial hub with the global economy. The roof structure, supported by a forest of sleek steel columns, was engineered for both visual lightness and structural strength, while large spans of glass maximized daylight without sacrificing thermal performance. Inside the terminal's shell, kilometers of electrical, plumbing, fire protection, and air handling systems had to be embedded with flawless precision. Every conduit and junction coordinated across dozens of contractors and engineering teams working simultaneously. The initial runway system was laid with equal attention to durability and volume. High-performance concrete was poured in long, uninterrupted sessions to create seamless surfaces for large-bodied aircraft. Drainage systems had to be designed not only for heavy rainfall, common in the region, but also for the complex water table beneath the reclaimed land. Pump stations, culverts, and storm channels were embedded into the very bones of the airport to ensure operations could continue during typhoons or seasonal flooding. Every phase was built with layers of redundancy, reflecting an understanding that resilience wasn't optional, it was foundational. As Shanghai's international profile soared, so did the scale of Pudong's ambitions. Terminal 2 was added in a massive expansion that more than doubled capacity, echoing the architectural language of the first terminal while integrating newer materials and systems. This phase included another runway, part of a broader plan to maintain aircraft flow without bottlenecks, and an underground transit network linking terminals and remote facilities. Construction crews worked in tandem with aviation authorities to ensure that all additions complied with evolving international standards, from runway safety zones to advanced baggage screening systems. The most striking construction achievement in later phases was the satellite concourse system. Gigantic structures linked by underground automated people movers. These satellite buildings weren't just appended. They were engineered to function as high-capacity extensions of the terminals, with full customs, immigration, and boarding infrastructure integrated underground and vertically. Building these while the airport remained fully operational required phased rollouts, nighttime shifts, and relentless coordination to avoid disrupting flight schedules. Some airports evolve slowly, layer by layer, molded by decades of growth. George Bush Intercontinental Airport in Houston, however, was born with a blueprint for scale from the very beginning. Constructed in the late 1960s to relieve pressure on the aging William P. Hobby Airport, IAH was never intended to be a simple regional terminal. It was a forward-looking investment, a modern answer to the booming oil economy and Houston's ascent as a global city. The site selected was expansive, a heavily forested stretch of North Houston that offered the space needed to dream big. Clearing the land was a massive undertaking on its own, requiring the removal of dense vegetation, rerouting of creeks and water flows, and the construction of entirely new utility corridors before the first runway could even be considered. Once the land was prepped, construction began with an ambitious but calculated layout. Instead of a single terminal, the airport would use a decentralized multi-terminal model, with each terminal functioning semi-independently while connected via road and eventually underground train. This modular design was intended to accommodate rapid expansion without crippling the core infrastructure. Each terminal could grow, be retrofitted, or replaced without overhauling the entire system. Early construction focused on 3 primary terminals, A, B, and C, each rising in parallel over poured concrete foundations and skeletal steel frameworks. The terminal buildings themselves were constructed with long-span trusses, allowing for wide, open concourses that minimized interior columns and maximized flexibility for airline operations. As the airport expanded, so too did its runways, crafted to handle the full spectrum of aircraft, including wide-body international jets and high-volume domestic carriers. Runway construction required extensive excavation and grading work to create a perfectly level base in Houston's famously unstable clay-heavy soil. Crews implemented multi-layered sub-base systems, including geotextile membranes, to prevent cracking and heaving from the area's intense rainfall and temperature swings. Parallel runways were spaced widely enough to allow simultaneous takeoffs and landings, an operational advantage critical to IAH's future role as a hub. Throughout the 1980s and 1990s, construction never truly stopped. Terminal C was expanded into a major domestic hub for Continental Airlines, and later, Terminal E was constructed as an international gateway. The development of Terminal E marked a shift toward high-capacity, high-efficiency construction. It featured dual-level road access, streamlined customs and immigration facilities, and modern jet bridges designed for next-generation aircraft. The supporting infrastructure was just as critical. New parking structures, maintenance facilities, and de-icing pads were all built to support the increasing traffic load. Simultaneously, the airfield lighting, navigational aids, and fueling systems underwent modernization to comply with FAA regulations and future-proof the site. Beneath the terminals, the construction of the airport's people mover system added a layer of subterranean complexity. Engineers bored deep into Houston's wet subsoil to install guideways and tunnels for the train, requiring continuous dewatering, careful slope stabilization, and waterproofing membranes to prevent long-term seepage and erosion. The result was a fully automated train system that allowed passengers to move between terminals without surface traffic interference, an operational necessity in an airport spread across thousands of acres. Every phase of expansion at IOH has demanded not just engineering expertise, but logistical acumen. The airport had to remain operational throughout each construction phase, meaning crews often worked overnight or in carefully isolated zones to avoid disrupting flight schedules. Coordinating contractors, security, utilities, and aviation authorities required a master-level orchestration of timelines and contingency planning. Yet through each stage, whether laying runway concrete under humid Gulf skies or welding steel at height, Houston's flagship airport grew into a true international gateway, one poured and riveted together by sheer logistical ambition. Amid the swirling dust and sun-baked plains of northern Egypt, where the echoes of antiquity still hum beneath the surface, a different kind of monument began to rise in the 20th century. Not one, carved from stone, but cast in concrete and steel. Cairo International Airport was conceived as Egypt's primary portal to the modern world, a replacement for the aging Al Mazaa Airport that could handle the soaring demands of commercial aviation in a capital rapidly expanding in population, influence, and ambition. From its inception, the project was steeped in logistical complexity, shaped by the challenges of working in a desert environment while tethered to the ambitions of a globalizing era. The early phases of construction focused on establishing the core infrastructure that would serve as the foundation for decades of layered growth. Located northeast of central Cairo, the site had to be fully excavated, graded, and serviced with basic utilities in an area that, at the time, lacked deep infrastructure. Massive swaths of earth were moved, and early work involved laying vast concrete aprons and taxiways capable of withstanding the punishing heat and seasonal extremes of the region. The soil conditions, arid and loosely compacted, required specialized engineering techniques to ensure long-term stability. Foundations were reinforced with deep footings and treated aggregate layers to mitigate shifting and cracking under the relentless Egyptian sun. Terminal construction began with a modular approach, an intentional strategy designed to facilitate future expansion without disrupting operations. Terminal 1, known in its early form as the Old Airport, was built with broad, open-plan halls supported by a reinforced concrete frame and long-span steel beams. The design prioritized resilience over aesthetics, focusing on airflow, structural simplicity, and load-bearing efficiency. Glass curtain walls and shading systems were introduced to reduce thermal gain while still allowing for natural light, crucial in a location where daytime temperatures often soared. As aviation volumes increased, the terminal underwent multiple expansion campaigns, each requiring retrofitting older structures with newer systems for baggage handling, ventilation, and fire safety, all while keeping the terminal partially operational. The addition of Terminals 2 and 3 marked a significant evolution in construction philosophy. Terminal 2, originally completed decades ago, eventually underwent a complete overhaul to bring it in line with international standards. This reconstruction was a feat of surgical engineering. The original frame was selectively demolished, and new sections were grafted into the existing structure. Contractors worked in tight, active zones, reinforcing aging concrete, integrating new seismic protections, and threading miles of electrical, plumbing, and HVAC lines through spaces never designed to hold them. Terminal 3, on the other hand, was a clean slate, constructed from the ground up as a state-of-the-art facility to accommodate wide-body aircraft and higher passenger volumes. Its frame was built from high-strength concrete and a steel roof truss system, supporting a terminal footprint that included dual-level departure and arrival flows, jet bridge systems, and a matrix of automated luggage belts built into a multi-tiered substructure. Beyond the terminals, Cairo's runways demanded careful engineering. Laid in parallel orientations to optimize wind handling and maximize simultaneous movements, the runways were constructed with high-durability concrete overlays and embedded lighting systems for all-weather operations. Groundwork involved excavation and subgrade stabilization across thousands of linear meters, requiring constant calibration to maintain level grading and load-bearing integrity. Runway expansions had to be synchronized with radar installations, air traffic control upgrades, and expanded taxiway systems to manage growing traffic without compromising safety or efficiency. Meanwhile, auxiliary construction, parking decks, maintenance hangars, fuel farms, and cargo facilities developed in parallel. Each support system required its own logistical plan, from fuel pipeline installations and fire suppression systems to cold storage zones for cargo handling. The cumulative effect was a sprawling, highly compartmentalized aviation complex whose every square meter had to be engineered for durability, redundancy, and heat resilience. Few megaprojects embody Cold War secrecy and Arctic engineering, like Norway's Olavsvern submarine base, an underground naval facility tunneled directly into a mountain just outside Tromsø, north of the Arctic Circle. This hidden fortress was conceived at the peak of NATO's strategic concerns in the North Atlantic and took decades of planning, excavation, and military coordination to bring into reality. Construction began in the late 1960s, driven by NATO's urgent need for a hardened naval base in Scandinavia to monitor and counter Soviet submarine movements in the Norwegian and Barents Seas. Olavsvern was designed from the outset to support both surface vessels and nuclear-powered submarines, offering them a completely secure and concealed operations hub within Norway's extreme northern geography. Engineers excavated over 25,000 cubic meters of solid granite to build the complex. The core of the facility is a massive internal dry dock, 300 meters deep into the mountain, capable of housing several submarines at once in total secrecy. Entry was via a camouflaged sea tunnel, nearly invisible from aerial or satellite reconnaissance, allowing vessels to slip in and out without detection. The entire complex was built with one purpose: survivability under sustained military threat. The mountain provided natural shielding against conventional and nuclear attacks, while internal blast doors and reinforced corridors added additional layers of protection. The dry dock could be sealed completely from the outside, and pressure systems maintained stable conditions even in the event of chemical or nuclear fallout. Inside the mountain, over 13,000 square meters of operational space was carved out and fortified. This included command and control rooms, crew quarters, repair workshops, fuel and weapons storage, and climate-controlled chambers for advanced sonar and electronic systems maintenance. The facility was fully self-sustaining, with independent power generators, freshwater reserves, and secure communication lines linking it to NATO's command network. Construction was carried out under extreme environmental conditions. Winter temperatures regularly plunged below freezing, and the surrounding fjords presented major logistical challenges for transporting materials and machinery. Specialized tunneling equipment had to be shipped in and adapted for Arctic rock conditions, while crews worked in shifts around the clock to meet strategic deadlines. The base was built not only to hide submarines, but to actively service and rearm them for extended missions. Fuel depots were constructed with double reinforced walls, and weapon storage areas were shielded against electromagnetic pulse effects. The internal rail systems moved torpedoes, spare parts, and equipment deep within the base without reliance on outside handling. Everything was streamlined for rapid turnaround under wartime conditions. Strategically, Olavsvern gave NATO forward positioning capabilities near Russia's northern fleet bases on the Kola Peninsula. Submarines stationed there could shadow Soviet movements, gather acoustic intelligence, and act as a deterrent in a theater where control of the Arctic sea lanes could shape the outcome of a global conflict. The level of investment in the base reflected the military significance of the High North. At its peak, Olavsvern was staffed by hundreds of naval personnel, including engineers, weapons technicians, and communications officers trained for cold weather warfare. It remained one of NATO's most classified assets throughout the Cold War, largely unknown even to much of the Norwegian public. What makes Olavsvern unique among submarine bases is not just its concealment, but its integration with the landscape. Unlike visible dry docks or floating depots, this installation was invisible until you were inside it. It combined Arctic geography, naval warfare, and fortress-level engineering into one seamless warfighting platform. Even after its deactivation in the early 2000s, the facility's infrastructure remains intact, ready, if necessary, to be reactivated for a new era of geopolitical tension in the Arctic. As competition over the polar regions intensifies, Olavsvern stands as a reminder that military megaprojects are often not just about weapons, but about geography, silence, and the ability to vanish beneath stone.
Every so often, a bridge goes up that's about more than just concrete and cables. It becomes a statement, a symbol of connection. And in the case of the Gordie Howe International Bridge, a long-awaited answer to a problem that had been frustrating two countries for decades. Stretching across the Detroit River, linking Michigan to Ontario, this bridge isn't just big. It's one of the longest cable-stayed bridges in North America, and easily one of the most significant pieces of binational infrastructure being built anywhere on the continent. What makes the Gordie Howe so fascinating isn't just its size or its elegant design, it's the sheer effort it took to make it happen in the first place. For years, traffic between Detroit and Windsor had relied almost entirely on the Ambassador Bridge, a privately owned structure that had become so overburdened and outdated that it regularly caused backups stretching for miles. And when your crossing handles more than a quarter of all trade between the US and Canada, that kind of congestion isn't just annoying. It becomes a real economic vulnerability. So the idea was simple: build a second bridge, publicly owned, with modern capacity and streamlined customs to keep people and goods moving. But nothing about getting it built was simple. Political resistance, lawsuits, funding fights, and international negotiations dragged the project out for years. In fact, the only reason it finally got off the ground was because both governments, on both sides of the border, realized that the stakes were just too high to keep waiting. The supply chains that run through Detroit and Windsor aren't just local, they're critical for everything from auto manufacturing to agriculture. And the Gordie Howe Bridge is designed specifically to handle that scale, with separate lanes for commercial and passenger vehicles, brand new customs plazas, and direct freeway connections on both sides. From an engineering standpoint, the project is stunning. The main span stretches more than half a mile between two massive towers, which themselves rise nearly as tall as some downtown skyscrapers. And because the Detroit River is both a busy shipping lane and an international waterway, the bridge has to offer enormous vertical clearance without the use of any in-water supports, which means all that load has to be perfectly balanced through its cables, anchored by foundations buried deep beneath the riverbanks. It's one of those designs that looks graceful from a distance but hides an incredible amount of technical muscle. And while construction is still wrapping up, the impact is already clear. Crews have reshaped entire neighborhoods, built new access roads, and installed the most advanced border control systems either country has ever used, all with the goal of making the border feel less like a bottleneck and more like a seamless connection point. The bridge is also being built with long-term resilience in mind, factoring in everything from heavy freight wear and tear to extreme weather and seismic forces. So when the Gordie Howe International Bridge finally opens to traffic, it won't just be another route on the map. It'll be the result of decades of waiting, fighting, planning, and engineering. And it'll stand as a monument to the idea that sometimes the biggest challenges require the boldest solutions, especially when they span a river, a border, and 100 years of history. Most airports are built on land that's already there. Kansai International wasn't. Instead, engineers created an entirely new island out in Osaka Bay, built an airport on top of it, and then had to figure out how to keep the whole thing from sinking into the sea. That's the challenge Japan took on when it decided to build Kansai International Airport, a project so bold and complex that it still stands as one of the most ambitious examples of modern infrastructure in the world. Back in the 1980s, Japan's major cities were bursting at the seams. Tokyo and Osaka needed more capacity for international air traffic, but there just wasn't enough available land near the city centers. Noise pollution was also a growing problem, especially with flights operating late at night. So planners came up with a radical solution. Instead of expanding on land, they would go out to sea and build an airport where planes could take off and land without disturbing densely populated areas. The result was Kansai International Airport, built on an entirely artificial island about 5 kilometers off the coast of Honshu. But the idea of building an airport in the middle of the ocean came with immediate engineering challenges. The seabed under Osaka Bay is soft, silty, and unstable, exactly the kind of ground you wouldn't choose for a massive, heavy structure like an airport. To make it work, engineers drove thousands of steel and concrete piles deep into the seabed to support the foundation, then placed layers of sand, gravel, and fill to shape the island itself. Even with that foundation in place, the island started settling almost immediately. Engineers had predicted that it would sink gradually over time, but not quite as fast as it did. Within the first few years, parts of the island had already dropped by several meters, forcing teams to constantly adjust and reinforce structures, utilities, and runway surfaces to keep them level and safe. And even now, decades later, the airport is still sinking, although at a much slower rate than before. Maintaining it has become an ongoing process that's just as important as building it in the first place. Despite the difficulties, Kansai International opened in 1994 with one of the most striking terminal designs in the world. The main terminal, designed by Italian architect Renzo Piano, features a long curving roof that mimics the flow of wind and water, a subtle nod to the airport's connection with the sea. It's functional too, allowing for efficient passenger flow and natural ventilation. The terminal stretches nearly 2 kilometers, and it was, at the time, the longest building on the planet. Getting to and from the airport is part of the experience. A dedicated rail link and an expressway connect Kansai to the mainland, running across a long bridge that becomes your first glimpse of the airport as you approach. And once you arrive, the open layout, sleek design, and ocean views remind you that you're standing on one of the most complex man-made structures on Earth. Kansai International wasn't just about solving an airport problem. It was a test of how far engineering could go when land, space, and geography are all working against you. And even though the project has been expensive to maintain, with ongoing challenges due to settlement, and typhoon exposure, it still stands as proof that sometimes the only way forward is to build where no one else has dared. Rising high on the Ethiopian plateau, more than 2 kilometers above sea level, Addis Ababa has always been a city of layers. Old and new, formal and informal, chaotic and alive. But over the past few years, the city has begun to take on an entirely new shape. The Addis Ababa City Corridor and Smart City Project is the centerpiece of that transformation, a sweeping plan to modernize the capital, expand its infrastructure, and create a blueprint for what a 21st century African metropolis can look like. At its heart, the project is about connection. Addis Ababa has grown rapidly, with millions of people moving in from rural regions, but the city's layout and infrastructure never quite kept pace. Roads became crowded, neighborhoods expanded without clear planning, and public services struggled to keep up. The City Corridor Plan aims to tie it all together, a network of modern boulevards, transit routes, and green corridors stretching across the city, designed to integrate housing, commerce, and technology in one continuous urban system. Think of it as both a transportation project and a digital backbone, built to link everything from the city's financial district to its emerging industrial zones. The smart city component is what makes it truly forward-looking. It's not just about widening roads or adding new buildings. It's about embedding intelligence into the fabric of the city itself. Sensor-based traffic management, integrated public data systems, and sustainable utilities that can monitor and adapt in real time. Streetlights powered by solar panels, automated waste collection, water systems that track usage and detect leaks, and transport routes that update dynamically based on congestion. All of these features form part of the vision. Addis Ababa isn't just being expanded, it's being reprogrammed. Alongside the technology, there's also a strong architectural and social vision. The new city corridors are planned to include dedicated pedestrian paths, landscaped parks, and mixed-use developments that bring homes, offices, and public spaces together. Rather than separating zones by function, the aim is to create integrated communities that reduce the need for long commutes and support more sustainable living. It's a response to the sprawl that has defined much of the city's past growth, turning what used to be dusty, disconnected suburbs into modern, connected districts. The construction itself is happening in phases, with local and international teams working together to upgrade transport corridors, build smart infrastructure, and prepare new land for development. It's a massive logistical challenge involving coordination between ministries, tech companies, and city planners, all while trying to minimize disruption in one of Africa's busiest urban centers. But despite the complexity, progress continues steadily, with visible changes appearing year by year. New roads lined with smart lighting, new districts emerging with coordinated urban layouts, and data centers forming the digital core of the city's new systems. What makes the Addis Ababa City Corridor project stand out isn't just its scale, but its symbolism. Ethiopia is positioning itself as a regional leader in technology and infrastructure, and the capital city is its proving ground. The project represents a shift from reactive urban growth to proactive, technology-driven design, an attempt to future-proof a city that's expected to keep growing for decades to come. And when it's complete, Addis Ababa could stand as one of the first truly smart cities on the African continent, built not just to handle its population, but to evolve intelligently alongside it. Toyota Music Factory in Irving is one of those places that feels like it was built for motion, for people coming and going, for crowds shifting from dinner to a show, for music spilling out onto patios on a warm Texas night. It sits right in the heart of Las Colinas, a district that's long been known for offices and corporate campuses, and it brings something completely different to the area: a pulse. The whole complex is designed around entertainment, food, and connection, creating a kind of urban village where everything happens in one spot. At its core is the Pavilion, the centerpiece venue that gives Toyota Music Factory its identity. It's not just an arena, it's an adaptable space that can transform depending on the size of the event. On some nights, it functions as an intimate indoor theatre for a few thousand fans, and on others, the back wall opens up to reveal a sprawling outdoor amphitheatre that can hold a crowd big enough to fill a small stadium. The engineering that makes that transformation possible is remarkable. Massive retractable panels, acoustic treatments that shift with the space, and lighting systems that adjust seamlessly from concert to open-air festival mode. Surrounding the pavilion is a grid of restaurants, bars, and smaller performance spaces that create a true district feel. The developers didn't just drop in a venue, they built an ecosystem around it. The pedestrian plazas are lined with wide shaded walkways, and there's always a hum of activity, whether it's people pre-gaming before a show or lingering afterward. The outdoor spaces are what really sell it though. Fountains, open lawns, and string-lit patios that feel casual but carefully planned. You can tell the goal was to make it just as enjoyable on a quiet Tuesday night as on a packed concert weekend. From an infrastructure standpoint, the Music Factory was a complex build. The site sits near major roadways and DFW airport flight paths, so engineers had to work around noise mitigation, traffic flow, and parking capacity for thousands of visitors. The parking structures were integrated into the design instead of pushed off to the edges, with direct pedestrian connections leading right into the heart of the plaza. The entire development sits on a mix of concrete and landscape decks, with stormwater systems built underneath to manage runoff from both the buildings and the paved areas. It's a good example of how entertainment architecture now has to balance spectacle with practicality. The acoustics and stage engineering inside the pavilion are worth mentioning too. Every panel, every curve was shaped to deliver sound that feels full and even no matter where you're sitting. Touring acts praise it for that reason. It's built for the modern touring circuit, flexible enough to host everything from pop concerts to stand-up comedy to orchestral performances without losing quality. But maybe the most interesting part of Toyota Music Factory is how it reshaped perception. For years, Las Colinas was known for its daytime crowd, business suits, office parks, conference centers. This project turned it into a place that stays alive after sunset. It gave the area a new rhythm and helped redefine Irving as more than just a stop between Dallas and Fort Worth.
Rising from Estonia's pine-covered plains near Tapa, Camp Rito represents one of NATO's most forward-deployed military megaprojects, engineered to support rapid reaction forces at the doorstep of Russia. This base was not built as a symbol, but as a highly functional logistics and combat hub, constructed to sustain prolonged operations in a high-threat environment. The strategic logic behind Camp Rito is clear. Estonia shares a direct land border with Russia. In the wake of renewed geopolitical tension in Eastern Europe, NATO required a hardened, rapidly deployable footprint on the eastern flank. Camp Rito was designed to host rotating multinational battle groups under NATO's Enhanced Forward Presence framework, enabling a permanent Allied presence without formal basing agreements. Construction began in the mid-2010s as part of a multi-phase infrastructure expansion program. The site was selected for its proximity to both rail and road arteries, as well as its access to the nearby Tapa military training area. Estonia's largest, allowing for live fire exercises and armored maneuver drills within minutes of the base perimeter. Engineers laid out the facility with modular expansion in mind. Pre-stressed concrete foundations were poured for over 100 buildings, including barracks, armored vehicle shelters, logistics warehouses, dining halls, ammunition storage bunkers, and maintenance depots. Many of these structures were prefabricated in segments to accelerate construction timelines and reduce supply chain dependency. Vehicle infrastructure was prioritized. Camp Rito includes reinforced roads capable of supporting tanks, IFVs, and heavy artillery under all weather conditions. De-icing systems were installed on key pathways to ensure mobility through Estonia's harsh winters. Fuel depots were built with dual-hardened containment systems, allowing the refueling of armored units on site without external support. The camp's power grid includes redundant diesel generators and battery arrays. Electrical wiring was embedded with EMP-resistant shielding, and communications were integrated into NATO's secure digital backbone. Satellite uplinks, encrypted fiber lines, and field-hardened server rooms were added to ensure uninterrupted command and control capabilities. Each barracks block is fitted with internal NBC filtration systems. Heating systems are fully winterized, with underground insulation around all water and sewage systems to prevent freezing. Tactical operations centers are located in reinforced concrete bunkers partially submerged for added blast protection. Water security was a key challenge. Engineers drilled deep bore wells and installed purification systems with triple redundancy, ensuring a clean water supply even during siege or isolation scenarios. Wastewater is processed on-site in a closed-loop treatment facility, compliant with NATO environmental standards. The base also includes a secure arms depot with access-controlled vaults, shock-proof internal walls, and fire suppression systems that operate independently from the base grid. Ammunition storage was built with blast relief tunnels, angled shafts designed to vent any accidental detonation away from personnel quarters. Camp Rito's design includes pre-surveyed landing zones for NATO helicopters and temporary pads for vertical lift drones. The outer perimeter is protected by layered defenses, anti-vehicle trenches, motion detection fencing, infrared surveillance, and pre-positioned rapid response points for mounted patrols. While multinational forces rotate through on a regular basis, primarily British, French, and Danish units, the camp is operated in close partnership with the Estonian Defence Forces. Every system, from vehicle compatibility to radio frequencies, was built for interoperability with Allied forces from the outset.
Most people think of Seattle and picture coffee, tech companies, and rainy skylines. But underneath all of that, there's been this slow-burning struggle to build a transit system worthy of the region's size, growth, and ambition. That's where Sound Transit 3 comes in. It's not just another local project, it's one of the largest transit expansions in the country. And it's meant to completely transform how people move across the entire Puget Sound region, not just today, but for generations to come. What makes Sound Transit 3 so different is the sheer scale of it. We're talking about over 60 new miles of light rail, pushing far beyond the current network, and reaching deep into communities that have long been isolated by traffic or dependent on slow buses and crowded highways. From Everett in the north to Tacoma in the south, and all the way out to places like Redmond and Issaquah, this is about stitching together an entire metro area with a spine of reliable, fast rail service that doesn't get stuck in traffic and doesn't rely on the constant expansion of roads. But it's not just about light rail. This package includes new bus, rapid transit lines, expanded commuter rail, more park and ride facilities, and even better, bicycle and pedestrian connections that feed into the bigger system. It's a kind of all of the above strategy that recognizes how sprawling and geographically complicated this region really is, with mountains, lakes, and waterways that make every mile of infrastructure harder to build and more expensive to maintain. And that's part of what makes this project so fascinating, because it's not easy, and the engineers and planners behind it are constantly balancing cost, complexity, and community needs in ways that few other cities have to deal with. Some of the most challenging parts are the tunnels. Building rail through central Seattle means going underground, and that means tunnel boring machines, deep excavation, and seismic design that can withstand the reality of living in an earthquake zone. Then there are the floating bridges. Yes, actual floating rail lines over water, which bring a whole new set of engineering puzzles, like how to keep railcars stable on a structure that literally moves with waves and weather. Every piece of this system has to be custom fit to the landscape, and that's why timelines stretch into the 2030s and beyond. What really drives Sound Transit 3, though, isn't just congestion relief. It's about shaping the future of how the region grows. With light rail stations comes development, density, and the chance to build neighborhoods around transit instead of highways. It's a blueprint for how to grow without choking on gridlock. And while it comes with a hefty price tag, voters backed it because the alternative was worse. A future where commutes get longer, emissions keep rising, and the economy starts to buckle under its own weight. There's a highway in Japan that cuts straight through Tokyo Bay, but it doesn't just go over the water like most bridges. It actually dives under it. This is the Tokyo Bay Aqua Line, a massive piece of infrastructure that connects the city of Kawasaki on the western shore to Kisarazu on the eastern side. And it does it with a combination of bridge, tunnel, and an artificial island sitting right in the middle of the bay. Before it opened, getting from one side of Tokyo Bay to the other meant driving all the way around it, which could take more than 90 minutes depending on traffic. The Aqua Line slashed that time down to about 30 minutes. That alone would be enough to justify a major investment. But to make it work, engineers had to go beyond traditional design and figure out how to cross one of the most heavily used bodies of water in Japan without disrupting the massive shipping traffic moving in and out of Tokyo's ports. So they split the structure in two. The first section, starting from Kawasaki, is a 4.4 kilometer bridge stretching out over the bay. Then, halfway across, the bridge ends on a man-made island called Umihotaru, which acts as both a rest stop and a transition point. From there, the road drops into a 9.6 kilometer tunnel that continues under the seabed and eventually surfaces in Kisarazu. That tunnel was one of the most technically demanding parts of the whole project. Digging a tunnel under the sea is never easy, but this one had to be done in soft soil while also accounting for seismic activity and saltwater corrosion. They used shield tunneling machines to dig through the seabed, installing thick concrete linings behind them as they went. The tunnel also had to be equipped with constant ventilation, pressure monitoring, and emergency access routes, since even a minor failure under that much water could be catastrophic. The artificial island, Umihotaru, wasn't just a place to change from bridge to tunnel. It was essential to the construction process. It provided a base for equipment, a place for workers to operate from, and eventually became a fully operational service area for travelers, complete with food, shops, and viewing platforms. It's also a venting station for the tunnel beneath. The Aqua Line officially opened in 1997, after roughly a decade of construction. And even though it was expensive to build and initially struggled with high tolls limiting traffic, it's become a vital connection for the region. It's also a showcase of Japan's ability to deliver complex infrastructure in harsh conditions, with multiple engineering disciplines, civil, marine, transportation, all working together to make it happen. Projects like this don't just solve traffic problems, they prove what's possible when design and execution come together at scale. But the real question is, would your country ever build something this ambitious? Or is this level of risk and investment unique to places like Japan? Let's hear what you think in the comments. If you've ever traveled through Britain by train, you know the experience can be both scenic and slow, with Victorian-era infrastructure still carrying millions of passengers every day. That's exactly what the HS2 project set out to change, a high-speed rail line designed to reshape how the country moves, connecting London with the Midlands and the North at speeds the UK has never seen before. It was imagined as the backbone of a new, modern transport network, one that could rival continental Europe's fast and efficient trains while easing the pressure on the country's crowded existing lines. High Speed 2, or HS2, is being built in stages. The first phase stretches from London to Birmingham, cutting travel times almost in half. The second was originally meant to continue north toward Manchester and Leeds, linking major cities with sleek new trains running at over 320 kilometers per hour. The ambition wasn't just about shaving minutes off journeys, it was about balancing Britain's economic geography, pulling growth and investment away from the capital and spreading it toward regions that had long been left behind. In theory, faster travel meant stronger regional economies, easier business connections, and new job opportunities across the country. But building HS2 has been anything but straightforward. It's one of the largest infrastructure projects in Europe, involving hundreds of kilometers of tunnels, viaducts, and embankments carved through some of England's most densely populated areas. The sheer complexity of the route required boring machines to tunnel under London suburbs, elevating tracks across countryside landscapes, and even designing specially built wildlife bridges to protect local ecosystems. Every section of the project is a microcosm of engineering challenges: soft clay, urban congestion, ancient infrastructure, and a constant balancing act between speed, safety, and sustainability. The construction workforce alone numbers in the tens of thousands, operating across dozens of sites at once. Giant tunnel boring machines, each named and tracked like ships, have been chewing their way through chalk and clay beneath the Chiltern Hills, creating vast underground passageways for the new line. Elsewhere, massive viaducts rise over river valleys, and new depots and stations take shape in cities that have been waiting decades for this kind of modernisation. Euston and Old Oak Common in London are being transformed into vast transport hubs, designed not just for HS2, but to connect seamlessly with existing networks, integrating the old with the new. However, despite its technical brilliance, HS2 has faced intense criticism and political turmoil. Costs have soared far beyond initial estimates, delays have stacked up, and parts of the northern extensions have been scaled back or cancelled entirely, leading many to question whether the project can still deliver on its original promises. Environmental groups have voiced concerns about the loss of woodland and natural habitats, while others argue that the benefits to the broader economy still justify the disruption. Even so, what remains of HS2 still represents a massive leap forward for Britain's rail system. When the first trains begin running between London and Birmingham, they'll mark the country's entry into true high-speed travel, a mode that much of the world has already embraced. And while the vision may have shrunk from its earliest days, the project still stands as a symbol of long-term ambition, the kind of investment that tries to build not just for today's commuters, but for generations yet to come. Ryan Tower at the University of North Texas at Dallas is one of those buildings that captures a moment of transformation, not just for the campus, but for the whole southern side of the city. It's a tall, striking landmark that stands above the low-rolling landscape, a visual anchor for a university that's still growing into its identity. You can see it from well beyond the campus, the glass and steel catching the light in a way that makes it feel like a symbol of movement and ambition. The tower is named after the Ryan Foundation, one of the key supporters behind UNT Dallas's expansion. It's not just a classroom building, it's a statement. When the project was conceived, the goal wasn't to build another generic academic space, but to create something that gave the university a clear presence, something people could point to and recognize as the heart of campus. For a long time, UNT Dallas was spread out and modest, a commuter school without a distinct center. Ryan Tower changed that. Architecturally, it rises with a simple, modern form, straight lines, reflective surfaces, and a vertical rhythm that contrasts against the wide-open Texas sky. The The materials were chosen to convey both durability and transparency. From the outside, the tower looks like a solid column of progress. From the inside, it's filled with natural light and open spaces that invite movement and interaction. The building's layout integrates offices, classrooms, and meeting areas with a focus on flexibility. Walls can be reconfigured, spaces can adapt, and the building feels alive in a way that's meant to evolve alongside the university itself. The engineering behind the structure is just as thoughtful as its appearance. The tower's frame was designed to handle wind loads that are typical for North Texas, with a reinforced core that provides stability while allowing the upper floors to stay relatively open and light. Energy efficiency was another major focus, using shaded glazing, efficient mechanical systems, and a building envelope that limits solar gain without cutting off daylight. It's the kind of detail that makes the building sustainable in the long term, both environmentally and economically. But beyond the technical aspects, Ryan Tower serves a deeper role. It gives UNT Dallas a sense of vertical identity. For years, most of the city's major academic institutions were located to the north, leaving southern Dallas underserved and often overlooked. The tower is a declaration that higher education belongs here too, that students in this part of the Metroplex deserve facilities that feel just as ambitious and inspiring as anything uptown. When you walk across campus and see the tower rising in front of you, it feels like a milestone, proof that the university has arrived. At night, the building takes on a different character. The interior lighting gives it a soft glow that can be seen from nearby highways, almost like a beacon. It's subtle, but powerful, an image of opportunity shining over a part of Dallas that's often hungry for it.
It began not with a single building or base, but with the largest American military construction project undertaken overseas since the end of World War II. Camp Humphreys, located in Pyeongtaek, South Korea, evolved from a modest airfield into the sprawling nerve center of U.S. military power in Northeast Asia, a transformation that required nearly 2 decades of relentless engineering, logistics, and international coordination. The expansion was initiated in the early 2000s as part of a strategic realignment between the United States and South Korea. The goal was to relocate the majority of U.S. forces from their vulnerable position in Seoul, just 40 miles from the DMZ, to a more defensible location farther south. Camp Humphreys, already housing a small contingent of U.S. personnel, was selected as the anchor site for this megaproject. The scope of construction was immense. Over 3,500 acres of land had to be secured, making it the largest U.S. military installation in the world by size. This required the relocation of several nearby South Korean villages, the rerouting of major roads, and a complex land reclamation process to prepare the site for development. The total area more than quadrupled, turning the base into a small city engineered for permanent, high-capacity occupation. More than 650 buildings were constructed, including headquarters for U.S. Forces Korea, family housing towers, barracks, schools, hospitals, logistics hubs, and training facilities. The site was master planned with the expectation of housing over 35,000 people, including soldiers, civilians, and their families. Infrastructure included not just military assets, but complete civilian support systems, utility grids, water treatment plants, retail centers, and even fire stations. To ensure uninterrupted operations under wartime conditions, the base was built with hardened command bunkers, redundant power supplies, and secure communications systems linked to the wider U.S. Indo-Pacific Command Network. Military logistics facilities included armored vehicle motor pools, aerial drone hangars, ammunition depots, and helicopter landing zones, all constructed to withstand both conventional and asymmetric attacks. One of the project's biggest engineering challenges was building on previously undeveloped and flood-prone land. Massive drainage systems were installed, along with deep foundations for major structures. Environmental impact mitigation required advanced soil stabilization and water diversion techniques to accommodate the region's heavy seasonal rains. Construction was overseen jointly by the U.S. Army Corps of Engineers and South Korea's Ministry of National Defense. At its peak, more than 17,000 workers were involved in daily operations, using heavy equipment and modular assembly techniques to accelerate progress. Prefabricated components were shipped in bulk from both domestic and international suppliers to meet deadlines and cost targets. The base is structured with a dual-purpose design philosophy: readiness and endurance. Warfighting infrastructure is integrated seamlessly with daily life systems. The command centers are located beneath reinforced buildings, while key logistical routes are protected by anti-vehicle barriers and surveillance perimeters. Internal road networks, emergency evacuation paths, and refueling points are all planned with conflict scenarios in mind. Strategically, Camp Humphreys is more than a relocation. It represents a long-term geopolitical bet. The base gives the United States deep operational reach into the Korean Peninsula, China, and the broader Indo-Pacific region. It acts as a launch point for rapid deployment, intelligence coordination, and allied joint operations, all while sitting well beyond immediate North Korean artillery range. The megaproject was funded largely by South Korea, covering roughly 90% of the multi-billion-dollar cost as part of the country's defense cost-sharing agreements. This level of investment underscores the strategic importance both nations place on the site, not just as a military base, but as a symbol of enduring alliance.
Not many projects in New York can claim they were first proposed during the Great Depression and still didn't see the light of day until the 21st century, but the 2nd Avenue subway wears that badge like no other. This wasn't just a transit line, it was a promise, passed from one generation of New Yorkers to the next, that one day, maybe, the city's most crowded corridor would finally get the relief it deserved. And after nearly a century of delays, cancellations, and false starts, the first phase finally opened in 2017, turning a long-running urban myth into a real, functioning piece of infrastructure. What makes this project so unique isn't just how long it took, but what it had to fight through along the way. The Upper East Side of Manhattan has always been one of the densest residential neighborhoods in the city, but for decades it had just one subway line, the Lexington Avenue line, doing the heavy lifting for hundreds of thousands of commuters every single day. Trains were jam-packed, platforms were bursting, and yet the idea of carving out a new subway down 2nd Avenue always seemed just out of reach. Every time funding was close, something went wrong. A war, a recession, a bankruptcy. Plans would be drawn, environmental reviews would begin, ceremonial groundbreakings would be held, and then the whole thing would collapse again. Rinse and repeat. When construction finally did begin for real, in the mid-2000s, it was no small feat. Digging tunnels through the bedrock of Manhattan is already complicated, but doing it under active streets, dense buildings, and some of the highest real estate values in the country raises the stakes to an entirely different level. Tunnel boring machines had to snake their way beneath existing infrastructure while crews managed utilities, avoided gas lines, relocated water mains, and stabilized buildings that were never designed to sit above a 21st century subway excavation. And then came the stations, not simple stops, but massive, cathedral-like caverns carved out of solid rock, deep beneath the surface. Each one had to be built with enough space to handle modern train volumes, with high ceilings, full accessibility, climate control, and finishes that actually made them feel like places people wouldn't mind spending a few minutes each morning. It was expensive, it was slow, but it was a level of attention to detail that set a new standard for American transit construction. When the first phase finally opened, running from 96th Street down to 63rd, it immediately started pulling riders off the Lexington line, easing crowding and proving that yes, the 2nd Avenue subway could work. But the job's not finished. Not even close. The full vision calls for extending the line all the way down through Midtown, the East Village, and into the financial district, creating a true second spine along Manhattan's east side. The next phase is already in motion, inching southward, and while the pace might still feel glacial, each new tunnel is another step toward finishing the job New York started almost 100 years ago. So the 2nd Avenue subway isn't just a train. It's a symbol of persistence, of finally delivering on a promise that should have been kept long ago. It shows what happens when a city refuses to give up, even if it takes an entire lifetime to get it done. There's something about the Dallas-Fort Worth area that never stops growing. Roads stretch wider, suburbs push further, and every year it feels like the region adds another layer of sprawl. But as the population surges and more cars hit the road, that old Texas strategy of just adding another lane isn't cutting it anymore. That's why the Southeast Connector project stands out, not just as another highway expansion, but as a massive, coordinated effort to untangle one of the most congested and complicated corridors in North Texas. If you've ever tried to drive through the southeast side of Fort Worth, especially during rush hour, you already know the pain points. Narrow lanes, outdated interchanges, and bottlenecks where 3 major highways collide. This is where I-20, I-820, and US 287 all come together, carrying everything from daily commuters to heavy freight. The volume is intense, and the existing infrastructure simply wasn't built to handle this kind of load. So instead of another patch job, TxDOT went big, with a full-scale reconstruction of over 16 miles of highway, rebuilding bridges, reconfiguring interchanges, and modernizing everything from pavement to storm drains. But this isn't just about traffic flow. It's about safety, too. The current configuration is full of sharp curves, short merging lanes, and weird transition points that make it one of the more accident-prone areas in the region. Part of the Southeast Connector's mission is to eliminate those hazards entirely, replacing outdated designs with smoother geometry, better sightlines, and wider shoulders that give drivers more room to breathe. It's the kind of redesign that doesn't just speed things up, it actively saves lives. One of the most impressive aspects of the project is the sheer amount of work being done at once. This isn't a staged, wait-and-see approach. It's an all-in, all-at-once operation. Crews are demolishing and rebuilding dozens of bridges, adding collector-distributor roads to separate through traffic from local exits, and widening lanes across the board to support long-term growth. And because this corridor is such a critical freight route, the new design will allow for a smoother flow of trucks, helping to unclog the supply chain and reduce delays that ripple far beyond DFW. Construction, of course, is never simple. There are major utility relocations, environmental protections for nearby creeks, and traffic management plans that have to keep thousands of vehicles moving even while everything is being rebuilt around them. It's like renovating a house while still living in it. Only the house is on fire and the kitchen is full of semis. But despite the challenges, progress is steady, with massive earth-moving equipment, steel girders, and towering cranes shaping a corridor that's going to look and function completely differently once it's done. In a region defined by cars, roads, and relentless growth, the Southeast Connector isn't just another construction zone. It's the blueprint for how North Texas plans to keep moving forward. And when it's finished, drivers won't just feel the difference. They'll see it in the form of safer ramps, shorter commutes, and the kind of infrastructure that finally catches up to the pace of the place it serves. Sometimes a project comes along that just doesn't make sense, at least not until you see it. drive across it, and realize what it actually represents. The Hong Kong-Zhuhai-Macau Bridge is exactly that kind of project. It's not just a bridge. It's not just a tunnel. It's a 55-kilometer long leap of engineering that crosses one of the busiest shipping lanes in the world, links three massive cities that used to feel far apart, and proves that China is willing to push infrastructure to extremes in ways few countries ever dare. To understand why it matters, you've got to look at the geography first. The Pearl River Delta is one of the most densely populated and economically powerful regions on the planet, with Hong Kong on one side, Macau on another, and Zhuhai anchoring the mainland. But even though these places look close on a map, getting between them used to take hours. Ferries, detours, congested roads. It was all slow, fragmented, and inefficient. So China decided to stitch the region together with a single mega link, one that could handle freight, commuters, and cross-border travel in one seamless shot. But building it wasn't simple. For starters, the bridge had to survive typhoons, earthquakes, and heavy marine traffic, all while standing in soft, muddy seabed that doesn't exactly love supporting massive pylons. Then there's the tunnel, because at one stretch, the bridge actually disappears beneath the water for over 6 kilometers to make way for ships. That required building 2 artificial islands out in the open sea, just so the road could dip down, dive under the shipping channel, and then rise back up again without interfering with maritime traffic. And that's where the engineering really hits you. The immersed tube tunnel, made up of huge prefabricated sections, was floated out, sunk into a trench, and sealed together underwater. Each section had to fit perfectly, with zero room for leaks or shifts. Above that, the bridge sections were hoisted into place using massive cranes, forming a ribbon of concrete and steel that curves and bends like a sculpture across the sea. When it finally opened in 2018, after nearly a decade of construction, the bridge cut travel time between these cities from several hours down to about 30 minutes. But beyond the time savings, it's a symbol. A signal that the Greater Bay Area is no longer just a loose collection of cities. It's becoming a single, interconnected mega region, one where borders blur and infrastructure drives integration. Of course, it hasn't been without controversy. The cost was enormous. The environmental impact was debated, and questions about who benefits the most continue to come up. But if you're talking about sheer ambition, about looking at a map and deciding to redraw it with concrete and cable, then the Hong Kong-Zhuhai-Macau Bridge stands in a league of its own. In the vast emptiness of northwestern Saudi Arabia, where desert and mountains stretch endlessly under the sun, a line of glass and steel is being drawn across the landscape. A city unlike any that has ever been built before. It's called The Line, and it forms the central vision of NEOM, a futuristic megaproject meant to redefine what urban living can be in the 21st century. The idea sounds almost impossible at first, a city that isn't sprawling outward, but extending straight for hundreds of kilometers, only 200 meters wide, yet home to millions of people. But that's exactly the scale of ambition Saudi Arabia is pursuing, nothing less than the reinvention of civilization itself. The concept behind The Line begins with simplicity. Instead of spreading a city outward in all directions, it compresses everything into a single linear corridor that runs through desert valleys and over coastal plains. The 2 mirrored walls of the city rise more than 400 meters, enclosing a narrow interior where people will live, work, and travel vertically rather than horizontally. The structure is designed to function as a continuous vertical metropolis where everything, from housing and offices to schools, parks, and public transit, is stacked efficiently inside a climate-controlled environment. At its core, the line is meant to operate without cars, roads, or traditional streets. Instead, it relies on a high-speed underground transport system that can move people from end to end in minutes. The idea is that every daily need, groceries, healthcare, education, recreation, should be within a 5-minute walk. By eliminating cars and long commutes, the designers aim to create a city where time is reclaimed for people, where nature and urban life coexist without one overwhelming the other. Sustainability sits at the center of the entire plan. The line is being built to run entirely on renewable energy, primarily from solar and wind power, and its compact footprint minimizes land use and environmental impact. The vertical design allows the surrounding desert and mountains to remain untouched, preserving natural ecosystems, while housing millions of people in a fraction of the space that a normal city would require. The structure's mirrored facade isn't just aesthetic. It reflects sunlight to reduce heat absorption and helps control the city's internal temperature. Engineering something of this magnitude pushes the boundaries of what's physically possible. The foundation requires precision construction over uneven terrain, and the structural demands of building two continuous walls hundreds of meters high across such distances are immense. The integration of transportation systems, data networks, energy grids, and vertical living spaces has to function seamlessly for the vision to work. Every part of the city will be monitored and managed through AI-driven systems, adjusting lighting, temperature, and logistics dynamically to optimize efficiency and comfort. The line also represents a broader idea about the future of Saudi Arabia. It's not just a mega project, it's a statement of national transformation. It reflects the country's drive to diversify beyond oil, to attract technology, investment, and global talent, and to present itself as a center of innovation. For the government, the line is both an economic experiment and a symbol of ambition, projecting the image of a nation willing to take risks to shape the next century. Whether it succeeds or not, the line is already changing the conversation about what cities can be. It's forcing engineers, architects, and planners around the world to imagine new forms of living, new ways of organizing society, and new relationships between humans and the environment. In the middle of the desert, a city that runs in a straight line may seem improbable, but that's precisely the point. It's a bet on imagination and on the belief that the future doesn't have to look anything like the past. Pacific Plaza in downtown Dallas is one of those rare public spaces that completely shifts how a city feels at ground level. For years, that part of downtown was little more than a patchwork of parking lots, office facades, and narrow sidewalks that people rushed through without stopping. Then came Pacific Plaza, a bold idea to turn a forgotten block into a real urban park, a green space that would invite people to slow down, gather, and actually experience the city in a new way. The park sits along Pacific Avenue, right in the heart of downtown's business district, surrounded by glass towers and busy intersections. What makes it special is how it manages to feel open and calm without being cut off from the energy around it. The designers didn't try to hide the city, they embraced it. You can hear the hum of traffic, see reflections of skyscrapers in the glass around you, and still feel like you've stepped into a pocket of peace. It's a rare kind of balance, one that most urban parks struggle to achieve. Pacific Plaza covers about 3.7 acres, but it feels much larger because of how it's shaped and layered. Instead of one big open lawn, the park unfolds in sections, planted groves, shaded walkways, small plazas, and a central lawn that becomes a gathering point for everything from yoga sessions to lunch breaks to evening concerts. The terrain rises and falls gently, giving the park a natural rhythm that plays off the straight lines of the surrounding buildings. One of the defining features is the massive wooden pavilion that stretches across part of the site. It's a sculptural structure made from warm, curved timber panels that filter light and create patterns of shadow across the ground. It's both shelter and symbol, an architectural gesture that ties the park together while offering shade in the Texas heat. Beneath it, people read, talk, and sometimes even nap, exactly what a good park should make possible. The project was also a victory for adaptive use. Much of the land that became Pacific Plaza had been surface parking for decades, a dead zone in the middle of downtown. Turning it into a park wasn't just about beautification, it was about reclaiming valuable real estate for public life. The transformation reconnected nearby buildings and opened up pedestrian routes that had been blocked for years. It gave downtown workers a reason to go outside during the day and residents a place to gather in the evenings. The materials are simple but durable: stone, wood, native grasses, and trees that can handle the Dallas climate. Everything about it was built with longevity in mind. Drainage systems are hidden beneath the surface. Lighting is integrated into the landscape, and maintenance was designed to be efficient rather than ornamental. It's a park meant to last, not one that needs constant upkeep just to look presentable. When you stand in Pacific Plaza today, you can feel how it changed the dynamic of downtown. It's no longer just an office district, it's becoming a livable one. Families stop by with kids, cyclists cut through on their way to Deep Ellum, and the place fills with a steady hum of life.
Hidden beneath one of the world's most populous cities lies a military megaproject so vast, it was once rumored to span hundreds of square kilometers. Known simply as the Underground City, this Cold War-era labyrinth beneath Beijing was a massive civil defense initiative. An entire subterranean metropolis designed to shelter millions of civilians and military personnel in the event of a nuclear conflict. Construction began in the late 1960s, at the height of tensions between China and the Soviet Union. Fearing an imminent Soviet nuclear strike, Chairman Mao Zedong ordered the creation of a vast underground shelter system that could serve as a fallback infrastructure for national survival. Officially called Dixia Cheng, the network was built largely by hand, using picks, shovels, and sheer manpower from Beijing's civilian population, including teenagers and retirees enlisted through Mao's mass mobilization campaigns. The underground system stretched for over 30 kilometers, connecting major government buildings, military, command posts, residential neighborhoods, and industrial zones beneath Beijing's streets. Some estimates suggested the full scale reached nearly 85 square kilometers at its peak, though much of that remains classified. The tunnels were built at depths ranging from 8 to 18 meters below the surface, reinforced with concrete walls and vaults to withstand air raids and limited nuclear blast effects. More than just tunnels, the complex was built as a full-fledged backup city. It included sleeping quarters, hospitals, food storage warehouses, classrooms, factories, and even theaters, all designed to function in isolation for months if surface life became uninhabitable. Independent water wells, air filtration systems, and power generation units were embedded throughout the structure to support long-term occupation. Ventilation shafts were camouflaged across Beijing, often hidden behind fake buildings or disguised as ordinary street features. The project's primary military function was continuity of government. In the event of a nuclear exchange, high-ranking officials, military commanders, and key personnel were to retreat into the network, from where they could maintain communication, organize civil defense, and direct counterattacks. The tunnels were also wide enough to allow small military vehicles and supply convoys to move underground, keeping logistics flowing even under bombardment. Much of the engineering followed the Soviet model of deep defense bunkers, but was adapted to the soft, clay-heavy soil beneath Beijing. To counter groundwater intrusion and soil shifts, crews installed thousands of tons of rebar and laid drainage pipes throughout the tunnel floors. In some areas, double reinforced ceilings were used to provide additional shielding against radiation and collapsing debris. The workforce was enormous. Reports suggest more than 300,000 civilian laborers participated in the digging over the span of a decade. Coordination was directed by military engineering corps, working closely with local Communist Party committees, and secrecy was paramount. Most workers were never told the full extent of what they were building. Though the Cold War threat that prompted its construction faded, the underground city remained partially operational into the early 21st century. Segments of the tunnel network continued to serve as military installations and civil defense shelters, while others were sealed off or repurposed. Some sections were briefly opened to tourists in the early 2000s before being shut again, possibly due to ongoing military use or modernization. The underground city exemplifies a distinctly Cold War logic. Prepare not just to fight, but to survive, rebuild, and reassert control from beneath the rubble. It was not a mere shelter. It was an engineered civilization beneath a capital, a megaproject designed to preserve command, culture, and cohesion during total war.
Sometimes the only way to fix a traffic nightmare is to dig right through it, and that's exactly what's happening under the waters of the Chesapeake Bay with the Hampton Roads Bridge Tunnel expansion, a project so massive and technically complex that it feels more like a feat of underwater surgery than roadwork. This isn't just about adding a few extra lanes or patching up a tired old road. This is about carving out a brand new tunnel system, right alongside the existing ones, and doing it all while millions of drivers still rely on this corridor every year to get in and out of Norfolk, Virginia Beach, and the rest of the Tidewater region. What's wild is that for decades, the original tunnels were just barely holding the line, 2 narrow lanes in each direction, squeezed by growing demand, constant military traffic, and a metro area that kept expanding while the bottleneck never changed. So now, instead of playing catch-up every few years, they're going big, with 2 new bored tunnels being drilled straight through the seabed, side by side, each wide enough to carry full interstate traffic and built using one of the largest tunnel boring machines ever deployed in North America. The machine itself is a behemoth, longer than a football field, with a rotating cutter head that chews through clay, sand, and bedrock like it's slicing through cake, pushing forward inch by inch while simultaneously laying down precast concrete segments to form the lining of the tunnel behind it. But tunneling is only part of the story, because above ground, the entire stretch of I-64 across the bridge tunnel complex is being widened as well, with new bridges rising from the water, traffic patterns being realigned, and interchanges being redesigned to finally eliminate the backups that have been part of daily life in this area for as long as anyone can remember. The work zones are intense, with crews working day and night on floating platforms, barges, and cranes, all surrounded by a working waterway filled with cargo ships, Navy vessels, and pleasure boats that can't afford to be delayed. Coordinating all of that without shutting down the region's economy or disrupting naval operations is a balancing act that requires military-grade logistics and relentless planning. And then there's the weather, because on top of the technical challenges, this is a region constantly exposed to hurricanes, tidal surges, and high winds, which means every element of this project, from the tunnel's waterproofing systems to the bridge expansion joints, has to be built with extreme resilience in mind. There's no room for shortcuts out here, not when lives, livelihoods, and national defense all depend on this corridor staying open. In the end, the Hampton Roads Bridge Tunnel expansion isn't just a fix for traffic. It's a massive leap forward in how this region connects with itself and the world beyond. Once it's finished, the flow of people, goods, and military readiness will all be transformed, not by one big moment, but by years of hard digging, steel lifting, and non-stop determination. And if you've ever sat in that bumper-to-bumper line, staring out at the water, wondering why it's taking so long to move, well, this is the answer. They're not just building lanes, they're building a future. It's not every day that you take one of the most iconic engineering achievements in human history and decide to tear it open, rebuild parts of it from scratch, and make it even bigger than before. But that's exactly what Panama did with its historic canal, a project so ambitious It was known simply as the expansion, and it pushed the limits of what was even possible in one of the most important trade corridors on Earth. For more than a century, the original Panama Canal had served as the narrow, vital artery connecting the Pacific and Atlantic Oceans. It was revolutionary in its time, slicing through the Isthmus of Panama and transforming global shipping. But as cargo ships got bigger, taller, and longer, the canal that once changed the world suddenly found itself stuck in the past. The largest container ships, the so-called post-Panamax giants, simply couldn't fit through. That meant Panama was missing out on billions in potential revenue, and the world's logistics network was increasingly having to go around. So in 2007, Panama broke ground on the biggest upgrade the canal had seen since it first opened in 1914. The centerpiece was a brand new set of locks, 3 chambers at each end of the canal that could handle ships more than twice the size of what the old locks were built for. But this wasn't just about size. The new locks used massive rolling gates instead of the old swinging ones, and they relied on water-saving basins that could recycle much of the fresh water used in each transit. In a region where water is precious and unpredictable, that was a game changer. Digging those new channels wasn't easy. Crews had to blast and excavate millions of cubic meters of rock, cut entirely new approaches, and do it all while keeping the original canal running full tilt. And because the canal operates on gravity and freshwater lakes, not pumps, every meter of elevation, every gate, and every water drop had to be managed with insane precision. The scale was mind-bending. Hundreds of kilometers of construction zones, dozens of engineering contractors from all over the world, and thousands of workers battling heat, rain, and mud year-round to make it happen. The expanded canal finally opened in 2016, after nearly a decade of work and a cost pushing over $5 billion. And the results were instant. Suddenly, ships carrying up to 14,000 containers could cross between oceans in under 10 hours. That single upgrade reshaped shipping routes, slashed costs for major carriers, and cemented Panama's role as a global logistics powerhouse. It also gave the country a new sense of ownership, because, unlike the original canal, which was built and long controlled by foreign powers, this expansion was run entirely by Panama itself, from the planning to the operations. It's one thing to build something great. It's another thing entirely to make it even better a century later, especially when the stakes are global and the margin for error is razor thin. In the quiet countryside of southern France, surrounded by pine forests and rolling hills, there's a construction site unlike any other on Earth. It's not another dam or bridge or skyscraper. It's a machine built to recreate the power of the sun. This is ITER, the International Thermonuclear Experimental Reactor, and it represents one of the most ambitious scientific collaborations in human history. The goal here is nothing short of mastering nuclear fusion, the same reaction that fuels stars, and turning it into a practical source of energy for our planet. The concept sounds simple in theory, but has pushed the limits of engineering for decades. Fusion happens when 2 light atomic nuclei, usually forms of hydrogen called deuterium and tritium, collide at extremely high temperatures and fuse into helium, releasing enormous amounts of energy. The problem is that replicating those conditions on Earth means creating and controlling plasma that's hotter than the core of the sun, about 150 million degrees Celsius, and keeping it stable long enough to extract useful power from it. That's where ITER comes in. At the heart of the project is the tokamak, a donut-shaped reactor designed to contain the plasma using magnetic fields so powerful they could lift aircraft carriers. The machine itself is a masterpiece of precision. Its vacuum vessel weighs over 5,000 tons. Its superconducting magnets are cooled to near absolute zero. And every component must align with millimeter accuracy, despite being the size of a small building. The idea is that when the system is fully operational, the reactor will produce 10 times more energy than it consumes. something no fusion experiment has ever achieved before. What makes ITER truly remarkable is how global it is. It's being built through a partnership of 35 nations, including the European Union, China, the United States, Russia, Japan, India, and South Korea. Each partner contributes different components, from cryogenic systems to magnet coils to diagnostic sensors, and all of them have to fit together perfectly when assembled in France. Coordinating that kind of international supply chain is an engineering feat in itself, with massive pieces of hardware shipped across oceans and transported by custom-built convoys that crawl through rural roads to reach the site. The scale of the infrastructure around the tokamak is equally astonishing. There's a massive cryoplant to cool the magnets, a system of vacuum pumps, cooling water loops, radio frequency heating systems, and an entire electrical network dedicated to feeding the experiment's colossal appetite for power. When ITER begins its first plasma runs, it will consume more electricity than a medium-sized city, though the aim is to prove that fusion can eventually produce far more energy than it uses. Yet the challenge isn't just technical, it's also philosophical. Fusion has been called the energy of the future for over half a century, and ITER's success or failure could finally determine whether that future is real. If it works, it could open the door to commercial reactors that generate clean, virtually limitless energy from seawater, with no carbon emissions and almost no radioactive waste. But for now, ITER remains an experiment, a monument to human cooperation and scientific persistence, standing quietly in Provence as thousands of engineers and scientists work to capture the power of the stars here on Earth. Garages of Texas at Lakeview in Dallas is one of those developments that only makes sense once you see it in person. A kind of private sanctuary built for people who love cars just as much as the space around them. It's not a dealership, and it's not a traditional storage facility either. It's more like a country club for car enthusiasts, designed around the idea that the garage itself can be just as important as the home. Every unit is privately owned, custom fitted, and treated like an extension of identity, turning what could have been a simple storage complex into a community built around horsepower, craftsmanship, and shared passion. The concept is deceptively simple: a gated complex of large climate-controlled garages that owners can buy, not rent, and outfit however they like. Some use them to keep vintage collections under perfect conditions. Others turn them into workshops, lounges, or even second offices. Each space starts as a blank canvas: high ceilings, polished floors, oversized roll-up doors, and a solid shell ready for personalization. From there, the customization begins. Owners add mezzanines, bars, display lighting, glass walls, or custom cabinetry, transforming raw square footage into something that feels personal and precise. The Lakeview location takes the concept a step further with its setting. It's built in a quiet pocket of North Dallas, tucked close enough to the city to be convenient, but far enough out to feel private. The surrounding area blends clean urban access with the openness of suburban layout, giving the garages the freedom to expand horizontally instead of being forced into a vertical or compressed structure. Wide drive aisles make it easy to maneuver collector cars, trailers, and lifts without stress. Everything about the layout feels like it was designed by people who actually understand what it's like to handle expensive cars. Construction quality is a major part of what makes Garages of Texas stand out. The buildings use thick, insulated walls, reinforced concrete slabs, and industrial-grade fire suppression systems. Temperature and humidity control are standard, protecting cars from the brutal Dallas heat and unpredictable weather swings. Lighting is another key detail: bright, clean, and positioned for clarity, not just ambience. It's a space where someone could detail a car at midnight and still see every reflection on the paint. But what's most interesting is the culture that's grown around places like this. Even though every unit is privately owned, The complex as a whole functions like a social club. Owners get to know each other, share projects, host open houses, or simply hang out and talk shop. On weekends, the sound of engines warming up fills the air as people roll out for car meets or test drives. It's part storage, part lifestyle, a place where ownership meets community.
Underneath 650 feet of Pennsylvania granite, the Raven Rock Mountain Complex, also known as Site R, stands as one of the United States' most fortified underground military installations. Located near Blue Ridge Summit, along the Pennsylvania-Maryland border, it was built during the early 1950s as a direct response to Cold War tensions and the looming threat of nuclear attack. Construction began in 1951, authorized by President Truman, with the explicit goal of creating a hardened alternate command center for the Department of Defense. If Washington, D.C. were ever incapacitated by a nuclear strike, key military operations could immediately shift to Raven Rock. The complex was completed in 1953 and activated under the supervision of the Army Corps of Engineers. The facility consists of a vast underground structure spanning several acres, with over 5 miles of internal roads. It contains 3 primary chambers, each roughly the size of a large aircraft hangar, dug directly into the mountain. These chambers house communications infrastructure, command centers, dormitories, offices, power systems, and storage facilities. The facility is capable of supporting up to 1,400 personnel in a fully sealed environment, with self-sustaining water reservoirs, diesel power generators, and air filtration systems designed to handle nuclear, biological, or chemical contaminants. Access is controlled through a heavily guarded portal sealed by 5 34-ton blast doors, each engineered to withstand nuclear shockwaves. Inside, everything from secure satellite uplinks to war room-level operations facilities remain on constant alert. The complex is linked by encrypted communication lines to the Pentagon, NORAD in Colorado, and other key defense installations, forming part of the larger U.S. continuity of operations plan. Site R is operated primarily by the U.S. Army, though it also supports joint military command functions involving the Navy, Air Force, and Marines. During the Cold War, it was directly tied into the National Military Command System and included in war game simulations for full-scale nuclear conflict. The facility has served as a communications relay, emergency response center, and alternate National Military Command Center. In modern times, Raven Rock continues to be staffed 24/7 and is one of the designated relocation sites for top military leadership. While it was originally envisioned as a Cold War contingency, it remains active today in the face of evolving threats including cyber warfare, EMP attacks, and large-scale terrorism. Its infrastructure has been upgraded repeatedly to include hardened digital systems and secure data nodes that integrate with national command networks. Though highly classified, occasional leaks and declassified documents have confirmed that Site R includes advanced telecommunications suites, a full medical center, armories, and a detention facility. It also has multiple escape tunnels, helicopter pads on the surface, and redundant logistical pathways for long-term isolation.
There's something about a massive river crossing that just captures the imagination, especially when it doesn't involve just one bridge, but an entire network of infrastructure rising together to solve problems that have been decades in the making. The Ohio River Bridges project, connecting Louisville, Kentucky to southern Indiana, wasn't just a plan to build some new lanes of traffic. It was a full-scale re-engineering of how two states move, grow, and interact every single day. And it took more than 10 years of grinding work, tough negotiations, and a whole lot of engineering creativity to make it all happen. Instead of tackling traffic congestion with a single fix, the project took a multi-pronged approach, building not one, but two new bridges, while also overhauling one of the most complex interchanges in the region. The downtown crossing included a brand new companion bridge next to the existing Kennedy Bridge, dedicated to southbound I-65 traffic, while the older bridge was rebuilt for northbound traffic. Meanwhile, the East End crossing opened up an entirely new corridor further upstream, finally delivering on a long-promised connection that helped relieve pressure on the downtown routes and opened the door for new development outside the urban core. And then there was Spaghetti Junction, the famously tangled interchange of I-64, I-65, and I-71, which had become a nightmare for drivers and a choke point for freight, completely redesigned and rebuilt to actually work in the 21st century. But this wasn't just a road building effort, it was a generational reshaping of the landscape, with crews moving earth, rerouting utilities, demolishing outdated structures, and threading new bridges through tight riverbanks and historic neighborhoods, all while trying to limit the impact on local businesses, homes, and daily commuters. At its peak, the project brought in thousands of workers, each playing a part in lifting steel segments into place over rushing water, pouring miles of concrete in punishing heat and cold, and operating massive cranes that swung silently through the night to avoid disrupting daytime traffic. What made the East End crossing especially challenging was the tunnel. Yes, a full-length tunnel burrowed through solid rock on the Kentucky side to preserve a historic estate and parkland, which meant engineers had to combine bridge building with tunneling expertise, groundwater management, and delicate excavation that pushed the limits of what local crews had tackled before. And while most people just see a bridge and think about the commute, the real story here is everything hiding underneath: the drainage systems, the geotechnical anchors, the seismic protections, and the realignment of roadways that all had to fit together like clockwork. It's easy to drive across one of these new spans today and take it for granted, but there's a reason the Ohio River Bridges project is still talked about as a model of regional cooperation, because it wasn't just a Kentucky project or an Indiana project. It was a shared commitment to finally solve a problem that had been kicking around for 50 years. And it's proof that even in an era of divided politics and strained budgets, big infrastructure dreams can still get built when people push hard enough and keep the long view in mind. There's a stretch of highway in southern France where drivers suddenly find themselves suspended in the sky, so high in fact that they're actually above the clouds. That's not poetic exaggeration, that's the Millau Viaduct, one of the tallest bridges in the world, and a megaproject that pushed both structural design and aesthetic ambition to new heights, literally. The story of the Millau Viaduct starts not with engineering, but with frustration. For years, travelers moving through the Tarn Valley, especially in the summer, were stuck in endless traffic jams around the town of Millau. The region's rugged terrain made road construction difficult, and the narrow valley routes couldn't handle the growing number of vehicles. A bypass was needed, and the only logical way to make it work was to go over the valley instead of around it. That's when the idea of a viaduct, a long bridge-like structure crossing the entire gorge, began to take shape. But this wasn't going to be any ordinary bridge. The span needed to be long enough to cross the entire Tarn River Valley in a single, clean sweep, and high enough to avoid disrupting the delicate environment below. That meant building a multi-span cable-stayed bridge more than 2.5 kilometers long, with a road deck floating nearly 270 meters above the river at its highest point. That's taller than the Eiffel Tower. And it's not just tall, the structure is elegant, sleek, and razor-thin, blending into the landscape with minimal visual weight despite its colossal size. The design was a collaboration between French engineer Michel Villelogeux and British architect Norman Foster. Villelogeux handled the structural genius, while Foster added the graceful visual language. Together, they created a design that looks light but performs under massive loads. The bridge has 7 pylons, each supporting a section of the deck with cables arranged in a fan pattern. The tallest pylon reaches 343 meters from the base to the tip, making it the tallest bridge support in the world. Building it required extraordinary precision. The deck was constructed in segments and launched outward from each pylon using a method called incremental launching. That meant carefully pushing out steel segments over thin temporary supports, balancing the structure as it stretched across empty space. Crews worked at incredible heights, often exposed to winds and weather, with every component measured to the millimeter. The alignment had to be perfect. Any misstep would throw the entire bridge off balance. The Millau Viaduct opened to traffic in 2004, and the transformation was immediate. The days of traffic crawling through Millau disappeared, and the journey across the valley became something drivers actually looked forward to. You don't just cross this bridge, you experience it. There's a moment, especially early in the morning, when the valley below is still filled with mist, where the road seems to float above the clouds. And for a few minutes, you're not just driving, you're soaring. But beyond the visual drama, the Millau Viaduct is a textbook example of how a mega project can solve a real-world problem while also becoming a piece of national pride. It's functional, efficient, and yet built with a sense of beauty that makes it far more than just infrastructure. Down on the shores of the Red Sea, where the old port city of Jeddah stretches out between desert and water, 2 enormous projects are quietly redrawing the map: Jeddah Central and Jeddah Economic City. Together, they represent a vision of transformation unlike anything the city has seen before, turning this historic gateway into a modern global hub for business, culture, and tourism. What makes these developments remarkable isn't just their scale, but the way they weave old and new, ambition and heritage, into something that feels distinctly Saudi, yet unmistakably international. Jeddah Central sits right in the heart of the city, taking over more than 5 square kilometers of waterfront that once housed the old desalination plant and underused industrial land. It's being reinvented as a new downtown, built around a sweeping marina and a waterfront district lined with cultural landmarks, residential towers, and entertainment spaces. The master plan revolves around 4 main landmarks: a sports stadium, an oceanarium, an opera house, and a museum, all designed to anchor Jeddah's identity as a cultural and leisure destination. Around them will rise luxury hotels, office towers, parks and promenades, all connected by shaded walkways and open public spaces, meant to bring life back to the seafront. But this isn't just about aesthetics. The project's layout is designed around sustainability and smart urbanism, integrating renewable energy, green transport systems, and water recycling technologies suited to the coastal climate. It's a major shift for Jeddah, which has long struggled with congestion and uneven urban growth. The plan envisions a livable, walkable downtown that balances modernity with comfort, turning the Red Sea coast into a showcase for the new Saudi lifestyle that's emerging under the country's Vision 2030 framework. The idea is to create not just buildings, but experiences, places where art, commerce, and everyday life blend seamlessly. A short distance to the north, Jeddah Economic City takes that ambition and scales it up to a global level. This is the site of the Jeddah Tower, the skyscraper that aims to surpass 1 kilometer in height and become the tallest building in the world. The tower is the centerpiece of a vast mixed-use development covering more than 50 square kilometers, designed to serve as a new economic hub for trade, finance, and innovation. When complete, Jeddah Economic City will have residential neighborhoods, educational institutions, business districts, and green open spaces all linked together by advanced infrastructure and digital systems. The city's design places a strong focus on integration with the wider region. Ports, highways, and logistics corridors will tie it directly into the national network, that connects Jeddah to Makkah, Medina, and eventually Neom, farther north. In many ways, Jeddah Economic City represents the country's broader push to diversify its economy beyond oil, creating new industries that can attract global investment and talent. Taken together, Jeddah Central and Jeddah Economic City show two faces of Saudi Arabia's urban transformation. One is cultural and civic, centered on lifestyle and heritage. The other is economic and technological, reaching for the future through engineering and ambition. Both are shaping a new identity for Jeddah, a city that once served as the gateway for pilgrims, now evolving into a gateway for ideas, enterprise, and modern urban life along the edge of the Red Sea. The Margaret Hunt Hill Bridge is one of the most recognizable landmarks in Dallas, a structure that turned what used to be an ordinary river, crossing into a signature symbol of the city. Stretching across the Trinity River, just west of downtown, it's a piece of infrastructure that became art, an unmistakable white arc rising high over the floodplain, pulling the skyline and the river together in a single dramatic line. When it opened, the bridge immediately changed how people thought about Dallas. For decades, the Trinity River had been treated as a kind of boundary, a place that divided downtown from the neighborhoods on the other side. The bridge turned that division into a connection. Suddenly, crossing the river wasn't just a commute, it was an experience. The single, massive steel arch at the center became the defining feature, rising nearly 400 feet into the air and holding up the deck below with a series of taut, graceful cables that seemed to hang like strings on an instrument. The design came from Santiago Calatrava, the Spanish architect and engineer known for his sculptural bridges around the world. He was brought in to help reimagine Dallas's Trinity Corridor, and the Margaret Hunt Hill Bridge was the first of his works to actually rise from that plan. It carries Woodall Rogers Freeway across the river, but calling it just a highway bridge doesn't do it justice. It's both functional and expressive, a kind of white ribbon that ties together two halves of a city that had long turned its back on the river. Structurally, it's a marvel of engineering precision. The arch doesn't sit directly over the roadway, it soars above it, leaning forward in a way that makes the cables fan out asymmetrically toward one side. This off-center suspension system was a huge technical challenge. Every load had to be calculated down to the smallest detail to make sure the deck stayed balanced, even though the support comes from only one side. The arch itself was fabricated from steel sections that were shipped in and welded together on site, each one shaped with incredible accuracy to keep the curve continuous from the base to the crown. During construction, the sight of the arch rising over the Trinity became a local event. For months, it stood half-finished, waiting for the final sections to be lifted into place, and people would drive out just to watch it take shape. When it was completed, it instantly became part of the city's visual identity, appearing on postcards, logos, and countless skyline shots. But what makes the bridge more than a photo opportunity is what it represents. It was part of a larger plan to revitalize the Trinity River corridor, to turn flood control levees and neglected land into parks, trails, and public spaces. The bridge became the physical and symbolic gateway to that transformation. Even as debates continue about how to develop the riverfront, the Margaret Hunt Hill Bridge stands as proof that the city can think on a grand scale and actually pull it off.
At the height of the Cold War, while the world stood on edge beneath the specter of nuclear annihilation, the United States embarked on one of its most ambitious military engineering projects, hollowing out the core of a granite mountain to build a fortress that could survive the end of the world. This became the Cheyenne Mountain Complex, a hardened command and control installation designed to absorb the unimaginable and keep operating. Excavation began in 1961 in Colorado Springs, Colorado, on the eastern slope of the Rocky Mountains. Engineers drilled and blasted through nearly 700,000 tons of solid granite, to carve out a vast internal network of chambers, tunnels, and infrastructure. The granite was selected not for beauty, but for density and stability. Its shock-absorbing properties were critical in the event of a nearby nuclear blast. Inside, 15 independent buildings were constructed, each mounted on over 1,300 steel springs, capable of swaying independently to absorb seismic shock. These buildings were not simply placed on bedrock. They were suspended within the mountain's hollowed core like floating islands of steel and concrete, isolated from the earth to maximize survivability. Each spring was rated to deflect up to 18 inches in any direction. The complex was designed to withstand a 30-megaton blast as close as 2 kilometers away. Blast doors weighing 25 tons sealed the entrances, and every major system inside had multiple redundancies. Air intakes were filtered through massive banks of scrubbers to remove radioactive, chemical, or biological contaminants. The water system drew from an underground reservoir, and backup diesel generators could keep the facility running independently for months. The construction took 6 years and involved thousands of workers, operating under extreme security and secrecy. Much of the interior concrete was poured under tightly controlled conditions to meet military specifications for strength and radiation shielding. Electrical systems were buried and shielded to resist electromagnetic pulses, and communication lines were hardened to maintain contact with key command centers like the Pentagon and NORAD's other facilities. By 1966, the Cheyenne Mountain Complex was fully operational. Its primary mission was to serve as the command center for NORAD, the North American Aerospace Defense Command, tasked with monitoring and responding to any missile threats against North America. Radar feeds, satellite data, and early warning systems all converged here, where military analysts tracked potential nuclear launches in real time and coordinated defensive responses. The layout of the complex includes over 4.5 acres of internal floor space. More than a mile of tunnels connects operation centers, data rooms, dormitories, dining facilities, and even a medical bay. Every piece of equipment was selected for durability under catastrophic conditions, and everything from door frames to wiring was built with the expectation that it might one day be tested in the most extreme scenario imaginable.
You could argue that no American infrastructure project has ever been more ambitious, more controversial, or more flat-out chaotic than the Big Dig. Officially known as the Central Artery/Tunnel Project, this wasn't just a highway job, it was a massive, decades-long attempt to untangle the concrete mess that had been strangling Boston for years. And in the process, it became one of the most complicated urban engineering efforts the country has ever seen. It all started with a problem that was painfully obvious to anyone who ever tried to drive through downtown Boston. The elevated I-93, known as the Central Artery, was loud, crumbling, over capacity, and a complete urban barrier, dividing neighborhoods and jamming traffic so badly that rush hour could stretch for half the day. So the solution? Bury it. Not just cover it or reroute it, but actually dig a brand new expressway deep below the existing one, right through the middle of a dense, historic city that was still very much alive above ground. And that's where things got wild, because you don't just drop a tunnel under Boston. You have to work around centuries-old buildings, subway lines, sewer mains, water pipes, electrical conduits, and ground conditions that are half landfill and half riverbed. Crews had to excavate around live rail tunnels, underpin massive structures so they didn't collapse, and deal with groundwater constantly trying to flood the site. In some places, the only way to keep digging was to freeze the ground solid with liquid nitrogen so it wouldn't cave in. The main tunnel itself wasn't even the only part. There was also the Ted Williams Tunnel, stretching under Boston Harbor to link up with Logan Airport. That section used a technique called immersed tube tunneling, where pre-formed tunnel sections were floated out into the water. sunk into a dredged trench, and then connected underwater like pieces of a giant Lego set. And let's not forget the Zarkum Bridge, a massive cable-stayed structure that became the visual symbol of the entire project, spanning the Charles River and replacing the old, rusted-out expressway ramps that used to dominate the skyline. But for all its engineering brilliance, the Big Dig became equally famous for its cost overruns, delays, political fights, and even tragic failures. What started with an estimate in the billions ballooned into over $14 billion by the time it was done, and there were lawsuits, construction flaws, and public outrage along the way. At one point, a tunnel ceiling panel collapsed, killing a driver and shaking public confidence in the entire effort. It was a reminder that even the best designs on paper can fall apart if the execution doesn't follow through. And yet, despite all of that, Boston is a different city because of the Big Dig. Where the old highway once split downtown in half, there's now the Rose Kennedy Greenway, a string of parks and open space that brought life back to the street level. Traffic flows better, the waterfront is more accessible, and the scars left behind by that massive elevated road have started to heal. In the end, the Big Dig wasn't perfect, but it was bold. It pushed engineering to its limits and redefined what a city could do when it finally decided to reclaim its own space. And maybe that's the real legacy, not just the tunnels or the bridges, but the idea that even the most broken infrastructure can be reinvented, if we're willing to dig deep enough to get there. In a country that's already known for doing things on a grand scale, Lucé City might be the most ambitious vision of all. It's not just another district or a new development on the edge of Doha. This is an entirely new city, built from the sand up, with skyscrapers, marinas, stadiums, and entire neighborhoods that didn't exist just a few years ago. And what's even more striking is that it was all designed to be ready in time for one of the biggest global events Qatar has ever hosted, the 2022 FIFA World Cup. Now, when most countries host the World Cup, they upgrade a few stadiums, maybe improve some roads, and polish the existing cities. But Qatar did something different. They decided to build a city, and not just any city, a futuristic, master-planned urban center that could one day rival major global capitals. That's Lucé. At the heart of it all is Lucé Stadium, a golden, bowl-shaped structure that became the centerpiece of the tournament. It held the opening and closing ceremonies, and it's where the world watched the final match play out in front of a roaring crowd. But Lucé wasn't built just for football. The stadium was only one piece of a sprawling urban puzzle that includes business districts, residential towers, tech hubs, shopping centers, and an entire waterfront lined with parks, walkways, and yachts. It's the kind of place designed not only to impress visitors, but to lay the groundwork for a post-oil economy. Something sustainable, modern, and globally connected. What makes Lucé stand out is how fast it all came together. Less than 2 decades ago, this was just empty desert. No roads, no buildings, just a bold vision and a whole lot of heat. And in that short time, workers and engineers transformed the landscape with underground tunnels, smart grid infrastructure, and cutting-edge cooling systems that keep the city livable even in Qatar's brutal summer. There's a light rail system that zips through the streets, fully integrated into the larger metro network, and nearly everything is designed with energy efficiency in mind. But as impressive as it is, Lucé also raises questions. Will people move there? Will the city thrive after the World Cup spotlight fades? Because building a city is one thing, filling it with life is something else entirely. Right now, Lucé still feels new, still in the process of becoming what it was meant to be. Office towers are waiting for tenants, apartments are waiting for families, and time will tell if it turns into the vibrant, buzzing metropolis that planners envisioned, or if it remains a symbol of ambition more than reality. Still, as a feat of engineering and construction, Lucé City is remarkable. It shows what's possible when you have the resources, the will, and a clear goal on the horizon. Tucked away in the mountains of Guizhou province in southwestern China, there's a gorge so deep and narrow that sunlight barely reaches the river at the bottom for most of the day. And spanning this massive cut in the earth, high above the mist and cliffs, engineers are building something that almost defies belief: the Huajiang Grand Canyon Bridge. When complete, it will stand among the highest bridges ever built on the planet. A structure so tall that if you dropped a skyscraper from the deck, it would fall for seconds before touching the valley floor. The numbers behind it are staggering. The bridge deck will rise over 600 meters above the river, which means it's taller than most observation towers and higher than the top floor of the Shanghai Tower. To put that in perspective, imagine stacking 2 Eiffel Towers end to end. That's roughly the drop from the roadway to the canyon below. This kind of height doesn't just make for dramatic photos, it turns every stage of construction into a feat of courage and precision. Workers spend their days suspended hundreds of meters in the air, guiding steel cables, assembling segments, and balancing heavy machinery on platforms that hang in the clouds. The Huajiang Grand Canyon Bridge is part of a new expressway that will connect cities across Guizhou, one of China's most mountainous provinces. Historically, this region was isolated by its terrain, deep valleys, twisting ridges, and karst formations that make road building incredibly difficult. The bridge is designed to close one of the biggest gaps, cutting travel times from hours to minutes, and linking communities that once felt worlds apart. In a province known for its poverty and difficult logistics, projects like this aren't just about transport, they're about access, trade, and opportunity. Structurally, it's a suspension bridge, chosen because it's one of the few designs that can handle both the span and the height of the canyon. The main span stretches more than 1 kilometer across, supported by enormous cables that anchor into the mountains on each side. The anchorages alone are buried deep in concrete and rock, absorbing the colossal tension forces that hold the deck steady. Every component must withstand fierce winds, extreme temperature shifts, and the constant pull of gravity across an open void. Even the construction of the towers is an achievement, with cranes and scaffolding perched on cliffs that would make most people's legs shake just looking down. What makes the Huajiang project even more impressive is how it reflects China's relentless drive to conquer geography with infrastructure. Guizhou has become a global showcase for bridge engineering, home to more of the world's highest bridges than any other region. Each one seems to push the limits a bit further. Higher decks, longer spans, faster timelines. The Huajiang Bridge is simply the next leap in that sequence, proving that there's almost no terrain too challenging to cross. When it finally opens to traffic, drivers will glide across a stretch of road that looks like it's floating between mountains, with clouds drifting below and the canyon yawning far beneath. It's one of those places where engineering and nature meet in a way that's both awe-inspiring and humbling, a reminder of what human ingenuity can achieve when the landscape dares us to go higher. The High 5 interchange in Dallas is one of those pieces of infrastructure that almost feels like a sculpture made out of concrete and steel. Rising more than 100 feet above the ground, where Interstate 635 meets US 75, it's an enormous tangle of ramps, columns, and sweeping curves that somehow fit together into one perfectly functioning machine. To the drivers who use it every day, it's just part of the commute. But to engineers, it's one of the most ambitious highway interchanges ever built in Texas. The name High 5 comes from the fact that it stacks 5 separate levels of traffic on top of each other. It's not just wide, it's vertical. Each layer handles a different movement of vehicles, weaving together north-south and east-west traffic without the stop-and-go chaos that used to define this stretch of road. Before the rebuild, this intersection was a nightmare of congestion, one of the worst in the state. Thousands of cars squeezed through narrow cloverleaf ramps, that couldn't handle modern traffic volumes, and the backup stretched for miles in every direction. When the Texas Department of Transportation decided to fix it, they didn't just widen lanes, they completely reinvented the interchange. The project called for nearly 3 million cubic yards of earthwork, more than 300,000 square feet of retaining walls, and an intricate arrangement of flyovers and bridges supported by over 30 massive piers. At its highest point, the top level rises roughly 12 stories above the ground, giving drivers a panoramic view of North Dallas as they sweep across in long elevated arcs. The engineering challenge was enormous. The construction had to be done while keeping traffic flowing through one of the busiest intersections in the region. Crews worked in carefully staged phases, shifting traffic patterns as new sections were built and old ones demolished. It was a kind of logistical ballet. Massive cranes lifting girders over live traffic, concrete pours happening overnight, and constant coordination to avoid shutting down major lanes during peak hours. What makes the High 5 interesting is how it manages to feel both efficient and elegant. The ramps curve smoothly, the columns are clean and evenly spaced, and the whole structure seems to float in the air instead of simply stacking slabs on top of one another. The geometry was refined through computer modeling to make sure every line of sight, merge point, and turning radius worked at highway speeds. It's a balance between engineering precision and visual clarity, something that's not easy to pull off at this scale. When it opened in the mid-2000s, the interchange immediately transformed the area. Traffic flow improved dramatically, cutting commute times and boosting development along both corridors. Businesses and residential complexes started rising nearby, drawn by the accessibility that came with a fully modernized highway system. For Dallas, it became a symbol of how serious the city was about mobility and infrastructure, an unmistakable reminder that this is a place built around movement.
Hidden beneath the chalk hills of northern France, the fortress of Megaprojects was one of Nazi Germany's most audacious military megaprojects, an underground artillery base engineered to bombard London with superguns from across the English Channel. Unlike V-1 flying bombs or V-2 rockets, this project relied on mechanical precision, underground fortification, and industrial-scale excavation to build a weapon system never before attempted in modern warfare. Construction began in 1943 under the code name Bovorhaben 711, following Hitler's directive to develop a massive fixed artillery installation capable of delivering continuous fire across 160 kilometers. The site was chosen for its geology. Chalk cliffs near the coastal town of Landreton-le-Nord offered easy tunneling, high elevation, and direct targeting alignment with London. The fortress was to house the V3, a fixed-position supergun that fired projectiles at extreme velocities using multiple explosive charges along a long barrel. To make this possible, German engineers tunneled vertically into the hillside and constructed 5 inclined shafts, each 130 meters long, angled toward England. These shafts were meant to house multiple V3 guns, with each barrel embedded into concrete-lined tunnels reinforced by steel supports. The design called for a rate of fire of up to 1 shell every 6 seconds once fully operational. Each projectile was small, but intended to be fired in such high volume that London would be under near-constant bombardment. The weapon's strength wasn't in its explosive yield, but in the psychological and logistical strain of sustained remote artillery assault. Fired from a mountain fortress no aircraft could easily destroy. The entire complex required over 30,000 cubic meters of material to be excavated, using forced labor from occupied territories. Dozens of auxiliary tunnels were carved to connect command centers, ammunition storage bunkers, power rooms, ventilation shafts, and rail lines to transport shells to loading points. A narrow-gauge railway system ran directly into the base, allowing munitions and building materials to be moved without exposure. Protection was a priority. The fortress was buried beneath up to 30 meters of rock and concrete in some places, with blast-resistant doors, anti-aircraft installations on the surface, and redundant access routes to allow continued operation during bombing raids. The design integrated underground living quarters, operations centers, and machine rooms to sustain long-term usage under siege conditions. One of the biggest challenges during construction was the sheer complexity of the V3 weapon itself. Each gun was composed of a series of secondary combustion chambers set at intervals along the barrel, timed to detonate in sequence to accelerate the shell as it moved forward. This required extremely precise engineering, complex ignition systems, and meticulous barrel alignment, all of which had to be installed underground in tight quarters, under the threat of constant Allied surveillance. As Allied bombing intensified in 1944, the Germans accelerated work. They diverted resources and labor from other V-weapon sites in a desperate bid to bring Megaprojects online. But the fortress was never completed. In July 1944, a series of massive Allied air raids, culminating in a strike by 12,000-pound tall-boy bombs, caused partial collapses and rendered the gun chambers unusable. German forces abandoned the site before it ever fired a shot. Despite its failure, the fortress of Megaprojects remains one of the most extreme examples of military engineering ambition during World War II. It was not just a weapon site. It was an underground artillery factory, fortress, and command center carved into a mountain with the singular goal of altering the course of the war through mechanical saturation bombardment.
You know, it's hard to even recognize parts of JFK right now if you haven't been in a while, because the place is changing faster than most people realize. And what's unfolding out there isn't just another round of airport renovations or cosmetic updates. It's one of the most ambitious and complex aviation overhauls ever attempted in the United States, with over $19 billion being poured into a complete reimagining of how millions of people move through one of the busiest air corridors on the planet. And what's really wild is that all of this is happening while planes are still landing, passengers are still moving, and operations are continuing 24 hours a day. At the center of this transformation is the creation of an entirely new Terminal 1, which is so big and so advanced that it's being built in phases like a city unto itself. And when it's finally done, it's going to be over 2 million square feet of sleek glass, steel, and high-tech systems designed to move international passengers faster, smoother, and with far more comfort than anything JFK has ever offered. And just to put that in perspective, that's about the size of 35 football fields stitched together, all meant to replace the aging Terminals 1 and 2 and part of Terminal 3, which were never really designed for the kind of traffic and pressure they're under today. But what's really impressive isn't just the scale. It's the way this entire redevelopment has been planned like a master puzzle, with Terminal 4 getting expanded for Delta to consolidate its operations, Terminal 6 being brought back from the grave and connected directly to JetBlue's Terminal 5 so passengers can finally have a seamless experience transferring between domestic and international flights, and the air train being upgraded to keep pace with the tidal wave of future demand. And when you think about how all of that has to be coordinated across separate contractors, airlines, funding sources, and public agencies, all while navigating insane logistical challenges like rerouting roadways and maintaining security zones, it becomes clear just how much engineering muscle and human coordination is being flexed behind the scenes. And of course, none of this is simple, because every time a new section opens or an old one shuts down, there's a ripple effect across the entire system, which means that construction crews, air traffic controllers, baggage handlers, and security personnel are all having to work around each other in this constantly shifting dance where timing is everything, and the margin for error is practically zero, because even a small delay in one part of the airport can throw off dozens of flights, hundreds of workers, and thousands of passengers, which is why this project is just as much about logistics and systems thinking as it is about steel and concrete. What's happening at JFK right now is nothing short of a reinvention, a complete teardown and rebuild of the way this airport functions from the ground up. And when it's all finished, the hope is that JFK will no longer be the overcrowded, outdated, chaotic experience that travelers love to complain about, but instead a world-class hub that reflects the scale and ambition of the city it serves. So the next time someone asks you why there are so many construction walls and detours at JFK, you can tell them it's because they're building the future, one terminal at a time. In the highlands of Ethiopia, right near the border with Sudan, a wall of concrete now stretches across the Blue Nile. A dam so massive that it's already reshaping not just the country's energy supply, but the politics of an entire region. This is the Grand Ethiopian Renaissance Dam, often shortened to GERD, and it's one of the most controversial and ambitious infrastructure projects in Africa's modern history. From a purely engineering standpoint, GERD is enormous. The main dam structure stands over 140 meters tall and spans nearly 2 kilometers across the Nile. Behind it, a reservoir capable of holding more than 70 billion cubic meters of water is slowly taking shape, making it one of the largest man-made lakes in Africa. And the hydroelectric potential is just as impressive. When fully operational, GERD is expected to generate over 6,000 megawatts of electricity. That's more than doubling Ethiopia's entire power capacity and turning the country into a potential electricity exporter for the whole East African region. But building this dam was never just about power. For Ethiopia, it's a matter of sovereignty and development. For decades, the country has relied on foreign energy imports and struggled to bring electricity to its rural population. GERD is seen as the key to unlocking long-term economic growth, creating jobs, supporting industry, and expanding access to power across millions of homes. It's a project that has been paid for largely through domestic funding, with the government encouraging citizens to invest in national bonds and support the construction financially and symbolically. That national pride, though, is matched by rising tensions downstream. Both Sudan and Egypt depend heavily on the Nile for irrigation, agriculture, and drinking water, and Egypt in particular has historically viewed the river as a lifeline. For generations, water treaties dating back to colonial times guaranteed Egypt a dominant share of the Nile's flow. Now, with Ethiopia holding back massive volumes of water behind a new dam, those old agreements are being tested. The fear from Cairo is that GERD could reduce the flow of water downstream, especially during the filling period of the reservoir, which could hurt Egyptian agriculture and water security. Ethiopia argues that the dam will actually help stabilize flow, reduce flooding, and benefit all three countries in the long term. But so far, years of negotiations haven't produced a final deal, and the disagreement has created real diplomatic friction, with threats, warnings, and political standoffs becoming more frequent. On the ground though, GERD is nearing completion. The first turbines are already spinning, and power is being delivered to the grid. Construction has taken over a decade, involving thousands of workers and a coordinated effort to bring in materials and equipment through difficult terrain. The logistics alone were staggering, given the remote location and the scale of the build. Whether GERD becomes a unifying symbol of African development or a long-term source of conflict depends on what happens next. Cooperation is still possible, but so is escalation. It's not every day you see a desert city trying to rewrite the global skyline, but that's exactly what's happening in Riyadh right now, as the Rise Tower begins to take shape. Planned to reach over 450 meters into the air, this soaring structure is meant to become the tallest building in Saudi Arabia's capital. and one of the tallest in the entire Middle East. But more than just height, Rise Tower is about a statement, one of ambition, reinvention, and a new kind of identity for a city that's transforming faster than most people realize. What's striking about this tower isn't just the glass and steel, it's the setting. Riyadh has always been a low-slung city built to survive the desert, a place of wide roads and sprawling neighborhoods. But Rise Tower is breaking that mold completely. It's anchoring the King Abdullah Financial District, a mega project that's aiming to turn the city into a global hub for finance and innovation. With futuristic architecture, high-tech infrastructure, and walkable urban design, right in the middle of the desert heat. Now, designing something this tall in Riyadh isn't as simple as copying a blueprint from New York or Shanghai. The tower has to deal with harsh sunlight, extreme heat, and powerful desert winds. So everything from its orientation to its skin is being engineered to handle those forces. Think of deep shading fins, high-performance glass, and an internal cooling system that helps balance comfort with sustainability. It's a blend of modern high-rise engineering and climate-specific design, and it has to work flawlessly to support not just offices, but residences, hotels, and observation decks stacked layer after layer up into the clouds. But there's also a symbolic layer to this. Rise Tower isn't just an office building with a fancy spire. It's part of a broader push to redefine what Saudi cities can be. It's coming at a time when the country is pouring trillions into development projects, from Neom to Diriyah. And Riyadh is being positioned as a global destination in its own right. So when you build a tower like this, you're not just constructing floors and elevators. You're constructing a future image, something that says, this is who we are now. And the engineering muscle behind it is just as intense as the vision. You've got mega piles drilled deep into the desert floor to support that much vertical load. You've got cranes operating at dizzying heights in a climate where metal burns to the touch by midday. Logistics, labor, safety, it's all being choreographed at a massive scale to keep everything on track. Because once you start reaching that high, every little mistake becomes a very big problem. The Margaret McDermott Bridge is one of those projects that shows just how much Dallas loves to think big, even when the road to getting there isn't smooth. Spanning the Trinity River, it was built as part of the massive Horseshoe Project, a sweeping reconstruction of the downtown Mixmaster interchange that handles some of the heaviest traffic in Texas. On paper, it was meant to be both an engineering upgrade and a visual statement, a combination of strength and sculpture that would redefine how people entered the city. The bridge itself carries Interstate 30, connecting the west side of Dallas to the urban core. It replaced an older, worn-out structure that had been straining under decades of use, and engineers saw a chance to do more than just rebuild. They wanted to create something iconic. The design was centered around two soaring steel arches, pure white against the skyline, curving gracefully over the river with cables dropping down to support the deck below. It was intended to be part of Santiago Calatrava's broader vision for the Trinity River corridor, linking up visually with the earlier Margaret Hunt Hill Bridge just to the north. But the McDermott Bridge wasn't just about looks, it was tied directly into the Horseshoe Project, a huge effort led by the Texas Department of Transportation to completely overhaul the tangled web of highways looping around downtown. The interchange between I-30 and I-35E had long been a nightmare. Tight ramps, short mergers, constant bottlenecks, and the project aimed to rebuild it from the ground up. Over several years, crews restructured bridges, realigned lanes, and rebuilt overpasses, all while keeping traffic moving through one of the busiest corridors in the state. The Trinity River itself adds another layer to the story. For decades, Dallas treated it more like a barrier than an asset, but projects like this have slowly started to change that. The McDermott Bridge was supposed to help turn the riverfront into something people could actually use and enjoy. It was designed with pedestrian and bike paths built into its structure, connecting to future trails and parkland along the floodplain. The idea was to make it not just a piece of infrastructure, but a public space, an everyday link between neighborhoods on both sides of the river. Of course, the road from a concept to completion wasn't perfect. The project faced cost overruns, delays, and some serious engineering challenges, particularly with the tension cables and wind performance of the pedestrian components. The bridge opened for vehicle traffic first, while the pedestrian sections took much longer to become safe and usable. But even with its complications, it stands today as one of the most recognizable features along I-30, its twin arches rising over the Trinity like giant gateways to the city. Together, the Margaret McDermott Bridge and the Horseshoe Project reshaped how people move through Dallas. The rebuilt highways relieved a notorious choke point. The bridge gave the skyline another landmark, and the Trinity Corridor gained another piece of its long-term transformation. It's a reminder that progress in a city this size rarely happens cleanly. It comes through persistence, revision, and a willingness to keep pushing until something lasting takes shape. Buried beneath the heart of London, there's a railway line that took more than 2 decades to go from vision to reality. And when it finally opened, it didn't just change how people travel across the city, it redefined what a modern urban railway could actually be. This is the story of the Elizabeth Line, better known during its construction as Crossrail, and it's one of the largest infrastructure projects the UK has ever attempted. What makes it so extraordinary isn't just the scale, though with over 100 kilometers of track and 10 brand new stations, the size alone is staggering. It's the complexity of tunneling through one of the most congested urban landscapes on Earth. London's underground is a tangled web of subways, sewers, gas mains, historic foundations, and centuries of construction. And Crossrail had to slide right through that chaos without disturbing the city above. That meant custom-designed, tunnel-boring machines carving through clay and chalk just inches away from existing infrastructure, operating with millimeter-level precision. And in the middle of all that, engineers were building cathedral-like stations deep underground, complete with massive concourses, soaring escalators, and sleek modern finishes that feel more like an airport than a subway. But it wasn't just about digging tunnels. Crossrail had to knit together a patchwork of existing railways to create a single high-capacity line running from Reading and Heathrow in the west, through central London, and out to Shenfield and Abbey Wood in the east. That meant not just physical connections, but totally revamping old lines, upgrading signals, rebuilding platforms, and bringing everything into one unified system. And because it's a hybrid of commuter rail and metro, the trains themselves had to be custom built, longer than anything else running in London. Fully walk-through from end to end, with cutting-edge safety and digital systems running the show behind the scenes. Of course, none of this came easy. The project was delayed, over budget, and constantly under scrutiny. It was originally meant to open in 2018, but it didn't fully launch until 2022. And even then, services were phased in slowly over time. But when it finally opened its doors, the impact was immediate. Journey times across London dropped dramatically. The central section now cut straight through the city in minutes, bypassing the old, overcrowded tube lines and offering a much smoother ride for millions of passengers. In fact, the Elizabeth Line has already become one of the busiest railways in the entire UK, and it's reshaping real estate patterns, job access, and urban development all along its route. At its core, Crossrail isn't just a transport upgrade, it's a statement. A bet that even in an old, densely built city like London, there's still room to dream big, to build something transformative, and to prove that world-class engineering can still punch through centuries of constraint.